Does time stop when you hit the speed of light? The lighthouse keeper's question. Picture, if you will, a lighthouse keeper on a storm-swept coast in the year 1887. The autumn wind howls outside his circular stone tower, rattling the glass that protects his beacon. Inside, surrounded by the warm glow of oil lamps, an elderly man named Thomas sits at his worn wooden desk, pen in hand, writing in his journal by the dancing light. But Thomas is no ordinary lighthouse keeper. By day, he tends to ships and sailors, guiding them safely home. By night, he contemplates the very nature of light itself. Tonight, as he watches his beacon sweep across the darkened sea, a question forms in his mind. A question that will echo through the centuries and touch the very heart of reality itself. What would happen, he writes in careful script, if I could somehow travel alongside this beam of light? Would time itself stop? Thomas doesn't know it yet, but his quiet wandering in that isolated tower mirrors a question that has captivated the greatest minds in human history. He doesn't know that 20 years later, a young patent clerk named Albert will ask himself the very same thing. He doesn't know that this simple, beautiful question will unravel the fabric of space and time itself. As the lighthouse beam continues its eternal dance across the waves, let us journey together through the centuries, following the golden thread of human curiosity that connects that windswept tower to the most profound discoveries about the nature of existence itself. The ancient dance of light and time. Long before Thomas sat in his lighthouse, long before clocks ticked on walls or Einstein dreamed of relativity, humans looked up at the night sky and wondered about light and time. In the fertile valleys between the Tigris and Euphrates rivers, where the first cities rose like dreams from the earth, the Babylonians watched the sun's daily journey across the heavens. They noticed something beautiful and mysterious. Light seemed to move. The sun rose in the east, traveled across the sky, and set in the west. The moon followed its own silver path. The stars wheeled overhead in their eternal dance. But how fast did light travel? Was it instantaneous, like a thought, or did it take time, like a bird crossing the sky? The ancient Greeks, those lovers of wisdom and beauty, pondered this question beneath olive groves and marble columns. Empedocles, a philosopher-poet who lived 2,500 years ago, imagined that light must travel from place to place, like a messenger carrying news from distant lands. He pictured rays of sunlight as invisible arrows shot from the sun's golden bow, racing across the cosmos to reach our eyes. But Aristotle, that great systematizer of knowledge, disagreed. In the cool shade of his Lyceum in Athens, surrounded by students hungry for understanding, he taught that light was not a thing that moved, but rather a condition, like wetness or warmth, that existed everywhere instantaneously. When the sun appeared, the space between sun and earth simply became illuminated. Just like when you enter a dark room and light a candle, the room doesn't gradually fill with light, it simply becomes bright. For nearly 2,000 years, Aristotle's voice echoed through the halls of learning. In medieval monasteries, where monks copied ancient texts by candlelight, scribes carefully preserved his words. In the great libraries of Baghdad and Cordoba, scholars debated his teachings under the light of oil lamps. The question of light speed seemed settled. Light simply was, everywhere at once, timeless and eternal. But in the gardens of the Islamic Golden Age, where fountains sang and scholars gathered to share their discoveries, new voices began to whisper of different possibilities. But the most beautiful discovery came when he studied the movement of shadows during eclipses. As the moon slowly crept across the face of the sun, Alhazen watched the shadows change. If light moved instantaneously, these shadows should change instantly too. But they didn't. They changed gradually, suggesting that light took time to travel from the sun to the earth. In his great work, The Book of Optics, written by the soft glow of oil lamps in his Cairo study, Alhazen made a bold claim: light has speed. It races through the heavens like a celestial horse, swift beyond imagination, but not infinitely fast. This single insight would plant a seed that would grow over centuries into our understanding of the very nature of time itself. As Alhazen's ideas spread along the trade routes, carried by merchants and scholars from Cairo to Damascus, from Baghdad to Cordoba, and eventually across the Mediterranean to the awakening universities of Europe, they carried with them a revolutionary idea that light and perhaps time itself were not the simple, obvious things they seemed to be. Renaissance Awakening, Galileo's first steps. Fast forward through centuries of war and plague, through the fall of Constantinople and the discovery of the New World, to a hillside in Tuscany in the early 1600s. The Renaissance has awakened Europe from its long slumber, and in the workshop of a brilliant inventor named Galileo Galilei, candles burn late into the night as he ponders the mysteries of motion and light. Galileo, with his wild hair and intense eyes, had already shocked the world by pointing his new telescope at the heavens and discovering that Jupiter had moons, tiny worlds dancing around the giant planet, just as planets dance around the sun. But tonight his attention turns to a more earthly question: how fast does light actually travel? Picture the scene: Galileo and his young assistant standing on two hills outside Florence, separated by about a mile of Tuscan countryside. Each man holds a lantern covered by a cloth. The plan is ingeniously simple. Galileo will uncover his lantern, sending light racing across the valley to his assistant. The moment the assistant sees the light, he will uncover his own lantern, sending light back to Galileo. By measuring the time between uncovering his lantern and seeing his assistant's response, Galileo hopes to calculate the speed of light. They try the experiment again and again on those cool Italian evenings, with the olive trees rustling in the breeze and the stars beginning to appear overhead. But each time the response seems instantaneous. Galileo's pulse, counted as a primitive clock, detects no delay at all. Is light truly instantaneous, as Aristotle claimed? Or is it simply too fast for their crude methods to measure? With characteristic honesty, Galileo admits defeat, but his conclusion is beautifully humble. He writes, "If light has speed, it is extraordinarily rapid." He doesn't know it, but he has just brushed against one of the fundamental constants of the universe, a speed so vast that it would take instruments far more sensitive than human reflexes to detect. But Galileo's failure contains the seeds of future success. For the first time in human history, someone has tried to measure the speed of light directly. The methodology is flawed, but the dream is sound: to pin down this mysterious, fundamental speed that governs the very fabric of reality. The Danish astronomer's breakthrough. Our story now takes us north, to the cold, clear skies of Denmark in the year 1676. In the Royal Observatory of Copenhagen, a young astronomer named Ole Romer bends over his telescope, watching something that will change our understanding of light forever. Romer isn't trying to measure the speed of light directly. Instead, he's doing something far more practical, creating better maps for sailors. The Dutch, those master navigators and traders, have offered a prize to anyone who can solve the longitude problem: how to determine exactly where you are when you're lost at sea. Romer believes the answer lies in the clockwork dance of Jupiter's moons. Night after night through Denmark's long winters, Romer watches Io, Jupiter's innermost moon, disappear behind the giant planet and emerge again on the other side. Like a celestial metronome, Io vanishes and reappears with clockwork precision every 42.5 hours. This regularity should make it perfect for navigation, a cosmic clock that sailors could use anywhere on Earth. Picture Romer in his observatory, wrapped in furs against the Danish cold, suddenly struck by a beautiful insight. Light itself must have speed. When Earth moves away from Jupiter, light from Io's eclipse has farther to travel to reach us, so it arrives later. When Earth moves toward Jupiter, the light has less distance to travel, so it arrives sooner. Working with the crude measurements available in 1676, Romer calculates that light takes about 22 minutes to cross the diameter of Earth's orbit. We now know his calculation was off. Light actually takes about 16.7 minutes to make this journey. But the principle is perfect. For the first time in human history, someone has actually measured the speed of light. The implications are staggering. Light, that most ethereal and mysterious phenomenon, races through space at about 186,000 miles per second. It's a speed so vast that light can circle the entire Earth more than 7 times in a single second. Yet, it's finite. Light takes time to travel. And if light takes time, then what we see of distant stars and planets isn't what's happening now, but what happened in the past. As Romer peers through his telescope at Jupiter's moons, he's looking not just across space, but across time itself. The light entering his eye left Io 43 minutes ago. He's seeing the past, preserved in golden rays of light racing across the cosmic void. Newton's particles and the mechanical universe. The story now shifts to England, where in the year 1687, beneath the apple trees of a Lincolnshire manor, one of history's greatest minds contemplates the nature of light and motion. Newton, fresh from his revolutionary discoveries about gravity and motion, turns his brilliant intellect toward the puzzle of light. In Newton's study, filled with prisms, telescopes, and sheets of calculations covered in his precise handwriting, light becomes a mechanical problem to be solved. Just as planets move through space following mathematical laws, light, Newton believes, must consist of tiny particles, corpuscles, racing through space like microscopic cannonballs. Picture Newton in his darkened room, allowing just a thin beam of sunlight to enter through a crack in his shutters. When this beam passes through a glass prism, something magical happens. The white light breaks apart into a rainbow of colors. Red, orange, yellow, green, blue, indigo, violet, the entire spectrum spreads across his wall like nature's own artwork. To Newton's mechanical mind, this makes perfect sense. White light must be a mixture of different colored particles, each traveling at slightly different speeds through the glass. The prism doesn't create the colors, it simply separates them, like a cosmic sieve sorting different sizes of grain. But Newton's particle theory of light creates a beautiful puzzle that will haunt physics for centuries. If light consists of particles racing through space at enormous speed, what happens when you try to catch up with them? What would you see if you could somehow travel alongside a beam of light? In the margins of his notes, Newton sketches thought experiments that seem almost magical. Imagine, he suggests, that you could run fast enough to keep pace with a beam of light. Would the light appear stationary beside you, frozen in space like painted streaks? Or would something else, something stranger happen? Newton doesn't know it, but his innocent thought experiment touches on one of the deepest mysteries in physics. His particles of light racing through the cosmos at 186,000 miles per second carry within them the seeds of a revolution that will reshape our understanding of space, time, and reality itself. As Newton carefully packs away his prisms and telescopes, the setting sun streams through his window carrying energy that left the sun's surface 8 minutes ago. In that golden light racing across his study lie the secrets of the universe, waiting for minds not yet born to unlock their mysteries. The wave revolution.
Our journey through time now brings us to a different kind of laboratory in a different kind of England. The year is 1801, and in a converted shed behind his house in London, a doctor named Thomas Young is about to overturn 2 centuries of Newton's authority with one of the most beautiful experiments in the history of science. Young isn't trying to disprove Newton, he reveres the great man. But as he works by candlelight in his makeshift laboratory surrounded by silk screens and carefully crafted apparatus, Young has noticed something that Newton's particle theory of light cannot explain. Light, he believes, doesn't behave like tiny bullets at all. It behaves like waves. Picture the experiment that will change everything. Young takes a beam of sunlight and passes it through 2 narrow slits cut in a piece of card. If Newton's right, if light consists of particles, then these particles should pass through one slit or the other, creating 2 bright bands on the screen behind. Instead, something magical happens. The light creates not 2 bands, but many, bright and dark stripes alternating across the screen like the ripples that form when 2 stones are thrown into a still pond. The light from the 2 slits is interfering with itself, creating patterns of constructive and destructive interference, just like water waves.
Young watches these patterns form on his screen and feels the thrill of discovery. Light isn't made of particles racing through space. It's made of waves, undulating through some mysterious medium like ripples on an invisible ocean. When the peaks of 2 light waves meet, they create brightness. When a peak meets a trough, they cancel out, creating darkness. But this discovery creates a new mystery. Waves need something to wave in. Ocean waves move through water. Sound waves move through air. What medium do light waves move through? Young and his contemporaries imagined space filled with an invisible, weightless substance they called the luminiferous ether, a cosmic jelly that fills the universe, allowing light waves to propagate from star to star. As Young writes up his discoveries by lamplight, he has no idea that his wave theory carries within it the seeds of an even greater revolution. For if light is truly a wave, and if waves have a fixed speed in their medium, then what happens when you try to catch up with a light wave? Can you ever take it? Can you see it standing still? These questions will obsess physicists for the next century, leading them down paths of discovery that will ultimately reveal the deepest secrets of space and time themselves. Maxwell's electromagnetic symphony. The scene shifts now to Scotland, to the mid-1800s, where a young man with an extraordinary mathematical gift sits before a fireplace in his family's estate, contemplating the invisible forces that surround us all. James Clerk Maxwell, with his thoughtful eyes and unruly hair, is about to weave together electricity, magnetism, and light into one magnificent mathematical tapestry. Maxwell had grown up fascinated by the hidden connections in nature. As a child, he would spend hours studying the patterns that iron filings made around magnets, watching how they formed beautiful curved lines like frozen music. He marveled at the way rubbing amber could make it attract feathers and paper. These weren't just curious tricks. They were glimpses of fundamental forces that shaped the universe. In his study, surrounded by books on mathematics and natural philosophy, Maxwell began to see the deep connection between electricity and magnetism. They weren't separate forces at all, but 2 aspects of a single phenomenon, like 2 faces of the same coin. When you moved a magnet near a wire, it created electricity. When you ran electricity through a wire, it created magnetism. They were partners in an eternal dance. But Maxwell's greatest insight came when he began to write the mathematical equations that described this electromagnetic dance. Working by candlelight through the Scottish winter nights, he discovered that his equations predicted something remarkable. When electric and magnetic fields changed, they created waves that raced through space at a very specific speed. Maxwell calculated that speed, and his heart must have stopped when he saw the number. Approximately 186
1,000 miles per second, the same speed that Romer had measured for light over 2 centuries before. The implication was staggering and beautiful. Light wasn't just light. It was electromagnetic radiation, waves of electric and magnetic energy dancing through space together. The warm glow of the fire in his fireplace, the light streaming through his windows, the stars twinkling in the Scottish sky, all were electromagnetic waves, differing only in their frequency and wavelength. Maxwell's equations revealed that this electromagnetic spectrum stretched far beyond visible light. There should be waves much longer than light waves and waves much shorter. The universe, Maxwell realized, was filled with an invisible symphony of electromagnetic radiation, most of which human eyes couldn't detect. As Maxwell penned his equations, those elegant mathematical expressions that would one day enable radio, television, and satellite communication, he included something that would puzzle physicists for decades to come. The speed of electromagnetic waves appeared to be constant, not relative to the motion of their source, not dependent on the observer, just constant. This seemed to violate common sense. If you throw a ball from a moving train, its speed relative to the ground is the speed you throw it plus the speed of the train. But Maxwell's equations suggested that light from a moving source would still travel at the same speed. It was as if the universe had a speed limit built into its very structure. The Great Ether Hunt. As the 19th century drew towards its close, Maxwell's electromagnetic theory created a beautiful puzzle that kept physicists awake at night. If light was truly waves moving through space, then space itself must be filled with some kind of medium to carry these waves, the luminiferous ether.
This ether would have to be extraordinary. It would need to be rigid enough to carry light waves at tremendous speed, yet thin enough that planets could move through it without slowing down. It would fill every cubic inch of space, from the gaps between atoms to the vast voids between stars. In Cleveland, Ohio, in the basement laboratory of Case Western Reserve University, two brilliant physicists named Albert Michelson and Edward Morley decided to hunt for this elusive ether. Their plan was elegantly simple. If Earth moves through the ether as it orbits the Sun, then light traveling in the direction of Earth's motion should behave differently from light traveling perpendicular to it. Picture their laboratory in 1887, the same year our imaginary lighthouse keeper Thomas was pondering the nature of light. In the basement, protected from vibration and temperature changes, sits the most precise scientific instrument ever built, the Michelson-Morley interferometer. The device works like an exquisitely sensitive race between two beams of light. Light from a single source is split by a half-silvered mirror, sending one beam in the direction of Earth's motion through space and another beam perpendicular to it. Both beams bounce off mirrors and return to recombined. If the ether exists, the beam traveling against Earth's motion through the ether should return slightly later than the perpendicular beam, creating an interference pattern. Month after month, Michelson and Morley run their experiment. They rotate their apparatus, trying different orientations. They repeat measurements at different times of day and different seasons of the year. They are hunting for the ether wind, the cosmic breeze created by Earth's motion through the invisible medium that fills space. But night after night, their results are the same. No matter which direction they point their light beams, no matter how Earth is moving through space, the speed of light remains absolutely constant. There is no ether wind. The interference patterns show no change at all. The result is so unexpected, so contrary to common sense, that Michelson calls it the greatest disappointment of my scientific career. They had built the most sensitive instrument in the world to detect something that, according to the best physics of the day, absolutely had to exist.
Instead, they found nothing. Or rather, they found something far more profound than nothing. They found that light doesn't need an aether at all. It travels through empty space at a constant speed regardless of how the source or observer is moving. This strange, stubborn constancy of light speed would soon shake the very foundations of physics. As Michelson and Morley packed up their equipment, wondering what had gone wrong with their measurements, they had no idea that they had just performed one of the most important experiments in the history of science. They had discovered a fundamental property of the universe itself, a cosmic speed limit that would soon revolutionize our understanding of space, time, and reality. The young patent clerk's dreams. While the physics establishment puzzled over the Michelson-Morley experiment, in the Swiss city of Bern, a young man with unruly hair and piercing eyes walked to work each morning along cobblestone streets, his mind churning with questions about space and time. Albert Einstein was 25 years old in 1905, working as a third-class patent clerk in the Swiss Patent Office. His job was to examine applications for new inventions, improvements to typewriters, designs for better mousetraps, proposals for more efficient brewery equipment. But as he sat at his wooden desk, surrounded by stacks of patent applications, his mind wandered to far grander inventions, thought experiments about the nature of reality itself.
Einstein had been thinking about light and motion since he was 16 years old. Walking through the countryside around Munich, he had imagined what it would be like to ride alongside a beam of light. If you could somehow keep pace with light, traveling at 186,000 miles per second, what would you see? According to Newton's physics, you should see light frozen beside you, like painted streaks in the air, electromagnetic waves standing still in space. But this created a paradox. Maxwell's equations said that stationary electromagnetic waves couldn't exist. They had to be moving to be electromagnetic waves at all. Something was wrong with this picture, and Einstein knew it. In his small apartment in Bern, as his wife Mileva helped care for their infant son Hans Albert, Einstein wrestled with this paradox. He read about the Michelson-Morley experiment and its puzzling results. He studied Maxwell's equations and their stubborn insistence that light always travels at the same speed. And slowly, like the dawn breaking over the Swiss Alps, a radical idea began to form in his mind. What if everyone had been asking the wrong question? What if the speed of light wasn't constant because it moved through some invisible medium? What if the speed of light was constant because space and time themselves were flexible? Picture Einstein in his study, surrounded by physics journals and covered in chalk dust from working out calculations on a small blackboard. The idea forming in his mind is so radical, so contrary to common sense, that it will overturn 3 centuries of physics. But it's also beautifully simple, elegant in the way that the most profound truths often are. What if time itself could slow down? What if space could contract? What if the universe was constructed in such a way that no matter how fast you moved, light would always race away from you at exactly the same speed? As Einstein began to work out the mathematics of this idea, he realized he was discovering something extraordinary. Time and space weren't the fixed stage on which the drama of physics played out. They were actors in the drama themselves, bending and flexing to preserve the cosmic speed limit that light represents. The birth of relativity. In 1905, that miraculous year that physicists now call Einstein's Annus Mirabilis, the young patent clerk published a paper that would change the world forever. Its title was deceptively simple, On the Electrodynamics of Moving Bodies. But within its pages lay a revolution that would reshape our understanding of the very fabric of reality. Einstein's special theory of relativity was built on 2 simple postulates, ideas so fundamental they seemed almost trivial. First, the laws of physics are the same in all reference frames that move at constant velocity. Second, the speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the light source.
But this created a paradox. Maxwell's equations said that stationary electromagnetic waves couldn't exist. They had to be moving to be electromagnetic waves at all. The most mind-bending consequence came when Einstein considered what would happen as you approached the speed of light itself. As your velocity increased, time would slow down more and more dramatically. At 90% the speed of light, time would pass about twice as slowly. At 99%, about 7 times more slowly. And as you approached the speed of light itself, time would slow toward a complete stop.
But here was the crucial point. You could never actually reach the speed of light. Einstein's equations showed that it would take infinite energy to accelerate any object with mass to light speed. The speed of light wasn't just fast, it was the ultimate cosmic speed limit, built into the very structure of space-time itself. As Einstein worked through the implications of his theory in his Bern apartment, he realized he had answered the question that had puzzled him since adolescence. What would you see if you could travel alongside a beam of light? The answer was both simple and profound. You can't. No matter how fast you travel, light will always race away from you at exactly 186,000 miles per second. The universe is constructed to make this impossible. Time dilation and the twin paradox. Einstein's revelation about time created one of the most beautiful and haunting thought experiments in physics. Picture two identical twins, born on the same day, growing up together, sharing the same bedroom, the same dreams, the same view of stars through their window at night. On their 25th birthday, one twin, let's call her Elena, becomes an astronaut and departs on a journey to a distant star. Her spacecraft accelerates to 99% the speed of light, racing through the cosmic void while her sister Anna remains on Earth, continuing her life as a teacher in a small town. From Anna's perspective on Earth, Elena's journey takes decades. She watches through telescopes as Elena's spacecraft dwindles to a point of light, carrying her sister across the galaxy at speeds that make light itself seem slow. During these long years, Anna ages normally. She watches her students grow up and have children of their own. Her hair turns gray, then white. Lines appear around her eyes, each one a story of laughter and sorrow, of seasons passing and returning. But Elena's experience is radically different. In her spacecraft racing through space at nearly the speed of light, time passes differently. What seems like decades to Anna feels like only months to Elena. Her clocks tick more slowly. Her heartbeat is measured by a different drummer. She ages just a few months, while her twin sister ages decades. When Elena finally returns to Earth, the reunion is both joyful and heartbreaking. Anna, now an elderly woman with grandchildren and great-grandchildren, embraces Elena, who has aged only slightly and could still pass for Anna's daughter. They are still twins, but time itself has pulled them apart, creating a gap that can never be bridged. This isn't science fiction, it's science fact. Einstein's equations predict this time dilation with mathematical precision, and experiments have confirmed it again and again. Atomic clocks flown on high-speed aircraft return running slightly slow. Particles called muons, created in the upper atmosphere, live longer when traveling at high speed than when at rest. GPS satellites must constantly correct their clocks because time runs slightly faster in their orbital altitude than it does on Earth's surface. As Elena and Anna hold each other in that imaginary reunion, they embody one of the most profound truths about our universe. Time is not the steady, unchanging river we imagine it to be. It's more like a stream that flows at different rates depending on how fast you're moving through space. The faster you go, the slower time becomes, approaching a complete stop as you approach the speed of light itself. The photon's journey, a being of pure light. To truly understand what happens at the speed of light, we must imagine something impossible, experiencing the universe from the perspective of light itself. Picture, if you will, the birth of a photon,
a particle of pure light in the nuclear furnace of a distant star. Our photon comes into existence in the star's core, born from the fusion of hydrogen atoms in temperatures of millions of degrees. From the moment of its birth, it possesses something unique in the universe. It has no mass, and therefore it must travel at exactly the speed of light. Not nearly the speed of light, not approaching the speed of light, but exactly 186,282,397 miles per second. It has no choice in the matter. The laws of physics demand it. But here's where the story becomes truly strange. From our photon's perspective, if we can imagine such a thing, its journey across space takes no time at all. Einstein's equations tell us that as you approach the speed of light, time slows down dramatically. At exactly the speed of light, time stops completely. Our photon experiences its entire existence as a single eternal instant.
Whether it travels from the surface of the sun to Earth, a journey of 8 minutes from our perspective, or across the galaxy, a journey of 100,000 years from our perspective, the photon experiences no time passing at all. From its point of view, it is created and absorbed in the same eternal moment, regardless of the distance traveled. This creates a beautiful paradox. The photon racing from that distant star to your eye as you read the story has traveled for perhaps thousands of years from our perspective. It has crossed the void between stars, perhaps passed by planets and asteroids, maybe even been bent by the gravity of massive objects along its path. Yet, from the photon's perspective, no time has passed. It was emitted by its parent star and absorbed by your retina in the same timeless instant. Space, too, behaves strangely from the photon's perspective. Length contraction, another consequence of Einstein's relativity, means that distances shrink in the direction of motion. At the speed of light, distances contract to zero. From our photon's perspective, the entire universe in the direction of its travel is compressed to a single point. It travels no distance at all. It simply exists everywhere along its path simultaneously. So what does a photon experience? The question itself may be meaningless. Our photon exists outside of time and space as we understand them. It is a being of pure light, dancing on the nice edge of existence, where the normal rules of reality break down and reveal their deeper, stranger truth. Time. It is the one thing that rules us all. We do not see it, yet it moves us. We do not hold it, yet it holds us. Every second that ticks away is another reminder of our mortality, another step forward into the unknown. But time is not just a human invention. It is woven into the very fabric of the universe. And so we ask the question, does time stop when you hit the speed of light? This question is not just science. It is history, philosophy, and imagination colliding in one burning mystery. It is a question that has haunted physicists, poets, and dreamers alike. To explore it, we must travel across centuries, from ancient philosophers who first asked what time even is, to Albert Einstein, who shattered our very perception of reality with his theory of relativity. And then beyond, into the infinite darkness of the cosmos, where light itself becomes the ultimate ruler. The ancient conception of time. Before rockets, before telescopes, before equations written on blackboards, humanity stood beneath the endless night sky, wondering. The ancients gazed upon the stars, watching the moon wax and wane, watching the sun rise and set, and they built their first understanding of time from these rhythms. For the Babylonians, time was marked by the dance of celestial bodies. The Egyptians built sundials, measuring shadows as if shadows themselves were the heartbeat of the world. The Greeks, with their philosophers, went further still. Was time a real thing, or merely a concept of the human mind? Aristotle believed time was a measure of change, a way of counting motion. Without motion, he argued, there could be no time. His student, Zeno, gave us paradoxes,
Achilles never catching the tortoise, an arrow frozen in mid-flight. Ideas that suggested time itself might not flow at all, but instead be an illusion made of infinite still moments. For centuries, these debates raged without resolution, but in every age, one truth persisted. Humans believed time was absolute. It marched forward like an unyielding river, the same for gods and mortals alike. That belief would hold until a man named Albert Einstein would come along and break it apart forever. The revolution of Einstein. The 19th century had been an age of clocks, trains, and synchronization. Railroads demanded precise timetables. Telegraphs sent signals faster than horses could ride. Nations began standardizing time zones. Humanity had bent the measurement of time to its will. And yet, beneath this progress, there was confusion brewing.
The fear and the temptation. The idea of time stopping has always haunted humanity. From the frozen arrow of Zeno's paradox to the dream of immortality, to live beyond time is both terrifying and seductive. If time could stop, could we escape death? Could we witness the birth and end of the cosmos as a single, unbroken truth? But here is the warning. Time is not our prison. It is our home. To leave it behind is to leave behind all meaning, all memory, all change. Without time, there is no story. Without time, there is no life. And so to ask whether time stops at the speed of light is not only to question physics, it is to question what it means to exist at all. But we are not finished. To understand fully, we must journey deeper into the mathematics of relativity, the experiments that proved it, the limits of human travel, and the strange frontier of black holes, where time also bends and warps like light. Only then can we stand at the edge of the universe, staring into the impossible, and ask again, does time stop at the speed of light, or does something even stranger happen? We left off standing at the edge of a revelation, that for light itself, time does not flow. But our journey does not end there. To understand what this truly means, we must go deeper, peeling back the layers of relativity, experiment, and imagination. For only then do we see the full shape of this strange truth. The elastic fabric of space-time. Einstein did not stop with special relativity. 10 years later, in 1915, he delivered a theory so bold it shook the foundations of science: general relativity. In this new vision, gravity was not an invisible force pulling objects together, as Isaac Newton had described. Instead, Einstein revealed that gravity was geometry itself. Massive objects bend the fabric of space-time, and smaller objects simply follow the curves of that distortion. Picture a bowling ball resting on a rubber sheet. The ball sinks the sheet downward. Now roll a marble nearby, and it will circle the ball, not because of some mysterious pull, but because it is following the bent shape of the sheet. So too with the planets, with stars, with galaxies. Space and time themselves are warped by mass and energy. And here again, time becomes elastic. Near a massive object, time slows. A clock on the surface of Earth ticks slightly slower than a clock orbiting in space. This is not theory, it is measurable fact. GPS satellites, high above Earth, experience time differently than we do below. If engineers did not account for this, your phone's navigation would be off by miles every single day. Time, it turns out, is not one universal heartbeat, but a shifting rhythm that depends on speed, mass, and gravity. The laboratory of the universe. If we want to understand what happens at light speed, we must look to the cosmos itself, for the universe has been conducting the experiments for us. Cosmic rays,
High-energy particles born in violent supernovae hurtle through space at speeds close to light. When they strike Earth's atmosphere, they create showers of particles that live longer than they should, because their clocks are slowed by their incredible motion. At CERN, the Large Hadron Collider spins protons to 99.99999% of the speed of light. In those moments, protons are not just bits of matter, they are messengers from the frontier of relativity. Their lifespans extend, their energy climbs toward infinity, and yet no matter how much power we pour into them, they never reach the barrier itself. The speed of light remains untouchable, a wall built in to the code of reality. For us, this may be a frustration, but for the universe it is necessity. Imagine if objects with mass could reach the speed of light. The laws of physics would unravel. Cause and effect would blur. The very structure of space-time would collapse. The wall at light speed is not a limitation, it is protection. The photon's world, a universe without time. And yet light does exist at that limit. What then is the world as seen by a photon? The answer is unsettling. In Einstein's relativity, distances contract as you approach light speed. To the traveler, space itself shrinks in the direction of travel. The faster you go, the smaller the universe becomes before you. At light speed, the distance collapses entirely. For a photon, there is no journey. A beam of light traveling from a star a billion light-years away to your eye experiences no distance, no time. From its perspective, emission and absorption happen instantaneously, at the same eternal moment. This is alien to our minds, for we live embedded in time. Our memories are chains of cause and effect. Our stories are born of before and after. But light has no such story. It simply is. When you gaze at the stars, remember, those photons have traveled billions of years through space. And yet from their own vantage, if we dare call it that, they never traveled at all. The twin paradox revisited.
James Clerk Maxwell had unified electricity and magnetism into a single, elegant theory, one that predicted light was not just a phenomenon, but a wave moving through space at a fixed speed, 299,792 kilometers per second. This was an extraordinary discovery, but it raised a troubling paradox. If light moved at this absolute speed, what happened if you chased it? Would you see it slow down? Would it vanish? How could its speed remain constant for everyone, no matter how fast they moved? Physicists struggled. They invented the luminiferous ether, an invisible substance thought to fill the cosmos, carrying light waves like water carries ripples. But the Michelson-Morley experiment of 1887 shattered that hope. No matter how they measured it, no matter which direction Earth moved through space, light always raced by at the same speed. The ether was a myth. Into this storm of confusion stepped a young patent clerk in Switzerland, Albert Einstein. In 1905, he published a paper that would change everything on the electrodynamics of moving bodies. In it, Einstein proposed something shocking. The speed of light is the same for everyone, everywhere, no matter how they move. The laws of physics must bend to preserve this truth. And from this simple postulate, an extraordinary revelation unfolded. Time itself is not absolute. It stretches, it warps, it bends. It is not the same for all observers. This was the birth of special relativity. Time dilation, when seconds become elastic. Imagine two twins. One remains on Earth, the other boards a spaceship that travels near the speed of light. For the traveler, time flows normally. Their heart beats, their watch ticks, they laugh and breathe as they always have. But when they return to Earth, they discover something staggering. Their twin is older. Decades may have passed on Earth while only a few years passed for them. This is time dilation, the slowing of time for those who move close to light speed. It is not fantasy. It is not science fiction. It is reality, proven in laboratories and particle accelerators. Muons, tiny particles created high in Earth's atmosphere, should decay in millionths of a second. And yet, because they travel close to light speed, their internal clocks slow down. They live longer than they should, reaching the surface of Earth. We have built atomic clocks, placed them on airplanes, flown them around the world, and when they return, their time is different. Not by much, but by enough to prove Einstein right. And so we creep closer to the question, what happens at light speed itself? The barrier of light. Einstein's equations reveal a brutal truth. As you accelerate closer to the speed of light, your mass increases. The faster you go, the heavier you become. The energy needed to accelerate further grows exponentially. At 99% of the speed of light, your mass is enormous. At 99.99999%, it is almost infinite. To reach 100%, to move at the speed of light itself, would require infinite energy. And so, no object with mass can ever reach it. Light alone, massless photons, may ride this ultimate speed. But let us imagine, what if somehow you did? What if you could ride alongside a beam of light touching the untouchable? Einstein himself pondered this as a teenager, imagining what it would mean to chase a light beam. If you could, would you see the wave frozen, unmoving? Would time itself stand still? The equations suggest something extraordinary. For the photon, there is no time. From the moment it is created in the heart of a star to the moment it collides with your eye across billions of light years, no time has passed. The photon does not age. It does not travel through time. For light, there is no past, no present, no future. And so, at the speed of light, time, as we understand it, ceases to exist. The human imagination at the edge. Pause and consider this. If time slows as you approach the speed of light, then at the limit, time itself halts. From the perspective of light, the entire history of the universe happens in an instant. Creation and destruction, stars born and dying, civilizations rising and falling, all compressed into a single eternal now. This is not merely physics, it is philosophy, it is poetry. What does it mean to exist outside of time? Could a human consciousness even survive such a perspective? Or would the mind shatter, unable to process eternity, collapsed into one infinite moment? We find ourselves brushing against the limits of science and stepping into the realm of wonder. Einstein himself was haunted by time. In a letter written near the end of his life, he reflected on the death of a friend, saying, "For us believing physicists, the distinction between past, present, and future is only a stubbornly persistent illusion." What did he mean? That in the grand fabric of space-time, every event, your birth, your death, the death of stars, already exists. Time does not flow, it simply is. The past, present, and future are all written into the geometry of the universe, waiting to be observed. This is the block universe idea, that all of history exists at once, and our consciousness simply moves along it like a needle tracing a record. If this is true, then perhaps at the speed of light, the needle no longer moves at all. Perhaps at that limit, the entire record is visible in one eternal instant. Causality and the speed of light. At the heart of the universe lies a law. Cause must come before effect. Light speed enforces this. It is not merely a barrier, it is the thread that keeps logic intact. Imagine sending a message faster than light.
Suddenly, what is cause for one observer may be effect for another. You could warn yourself of events before they happen. You could kill your own grandfather before your birth. These paradoxes tear apart the fabric of reason. And so the cosmos protects itself. The light barrier is not arbitrary. It is the skeleton of causality. Break it, and the universe collapses into contradiction. This is why physicists, even when dreaming of faster-than-light travel, tread carefully. They speak of loopholes, of bending space, rather than racing through it. For to move faster than light directly is to step outside the story of time itself. Warp drives and wormholes, dreams of escaping time. Yet humans have always been dreamers. And so, scientists and storytellers alike have imagined ways around the barrier. One is the warp drive, popularized by science fiction but grounded in real equations. Miguel Alcubierre, in 1994, showed that relativity's mathematics allowed for a bubble of space-time that contracts ahead of a ship and expands behind it. The ship itself never moves faster than light relative to its bubble, but the bubble can carry it across space at apparent superluminal speed. In such a scenario, time dilation might be bypassed. The traveler could cross light years without aging centuries, but the cost is staggering. It would require negative energy, exotic matter not known to exist. Some say the energy needed is greater than that of the entire universe. Others refine the math, searching for loopholes. The dream persists. Then there are wormholes, tunnels through space-time, shortcuts from one point to another. General relativity allows them in theory. Kip Thorne, the physicist who inspired the film Interstellar, explored them seriously. A stable wormhole could connect distant stars, perhaps even distant times. For here lies another possibility. Wormholes could allow time travel. One mouth of the wormhole, accelerated close to light speed, would experience time dilation. The other, left behind, would not. Step through, and you emerge not only in another place, but in another era. Past and future linked by a cosmic tunnel. And yet again, the universe whispers its warning. Wormholes may collapse instantly. Exotic matter may be required to keep them open. Quantum instability may tear them apart. Still, the idea beckons. For to dream of faster-than-light travel is to dream of mastering time itself. Quantum physics and the illusion of time. While relativity paints time as flexible, quantum mechanics raises a darker question. Does time even exist? Some physicists argue that time is not fundamental. In the equations of quantum gravity, attempts to unite Einstein with the quantum world, time sometimes disappears entirely. The universe is described as a timeless wave function, with time emerging only when certain conditions are met. If this is true, then asking whether time stops at the speed of light may be the wrong question. Time may be nothing more than a construct, a shadow of deeper laws. To the photon, there is no time, because perhaps time itself is not real at that level. Others suggest that consciousness creates the flow of time, that our minds stitch together moments into a sequence, giving the illusion of passage. Without observers, there may be no before or after, only an eternal quantum dance. These are unsettling ideas. They challenge not just physics, but the meaning of life itself. If time is an illusion, then what then is death? What is memory? What is the soul? The psychological weight of time.
One twin boards a spaceship and accelerates close to light speed. The other remains on Earth. When the traveler returns, they are younger. At first glance, this seems impossible. Shouldn't both twins see the other as moving, and thus aging more slowly? The resolution lies in acceleration. The traveler must speed up and slow down, breaking the symmetry. In doing so, their experience of time is warped. What seems paradoxical at first
becomes clear when examined through relativity's equations. But the emotional weight of the paradox lingers. Imagine returning to Earth after what feels like a few years, only to find centuries have passed. Loved ones gone, civilizations changed. You remain young, but the world you knew is dust. Time dilation is not only a scientific truth, it is a human tragedy waiting to unfold. Black holes, where time stands still. If there is anywhere in the cosmos where we can glimpse what it means for time to stop, it is at the edge of a black hole. A black hole is the ultimate concentration of mass. Its gravity is so intense that space-time curves back upon itself, forming a boundary from which nothing can escape, the event horizon. As you approach this horizon, something remarkable happens. To a distant observer, your time slows. Your movements become sluggish. Your signals stretch and fade. At the very edge, you appear frozen in place, suspended forever at the brink of falling. From your own perspective, time flows normally. You cross the horizon and fall inward, perhaps to the singularity where the known laws of physics collapse. But to the outside universe, you never quite arrive. You are trapped in a kind of eternal limbo. It is here, at the edge of black holes, that time itself becomes a battleground. Some physicists argue that information is trapped forever. Others say it leaks out slowly as Hawking radiation. Still others dream that black holes may be gateways to other universes, where time plays by different rules. But all agree on this. Near these monstrous objects, time bends to its breaking point. The human obsession with stopping time. Why does this idea captivate us so much? Because time is the one enemy we cannot defeat. Empires rise and fall. Kings and prophets come and go. Civilizations burn and are rebuilt. The one constant is the march of time. And so, across cultures, myths arose of frozen moments and immortality. In Japan, tales of Urashima Taro tell of a fisherman who visits a magical undersea palace only to return and find centuries have passed. In the West, Rip Van Winkle slept for 20 years, awakening to a changed world. Time dilation was already part of our stories long before Einstein gave it mathematical form. The dream of stopping time is the dream of escaping death. If we could ride the speed of light, if we could escape the river of seconds, perhaps we could live forever. But the price of such a dream is steep. To stop time is to step outside of life itself. For life is motion, life is change. Without time, there is no heartbeat, no thought, no love. And so the paradox, we long to escape time, yet we are nothing without it. The speed of light as cosmic law. Everywhere we look, the speed of light emerges as a boundary. No signal can travel faster. No event can overtake it. It is woven into the equations of relativity, into the very way causality works. If faster than light travel were possible, time itself could run backward, cause could follow effect, paradoxes would erupt, killing your grandfather before your birth, sending messages that erase themselves, collapsing logic itself. The universe, it seems, guards against this chaos by enforcing light speed as the ultimate limit, not merely a speed, but a law, not merely a boundary, but a foundation. It is humbling to realize the light that warms your face, the light that paints the dawn sky, that light is not only energy, it is the speed limit of existence. And yet, our story is not done. For though no mass may reach light speed, human imagination refuses to stop. What if there are loopholes? What if there are paths around the barrier, wormholes or warp drives or dimensions beyond our own? If time stops at light speed, what happens beyond? Could there be realms where time flows differently or not at all? Could eternity be touched, if only in theory? To answer, we must journey further still, into the strange frontier of modern physics where quantum mechanics collides with relativity, where dreams of faster-than-light travel dance with paradox, and where the fate of time itself may lie hidden in the deepest laws of the cosmos. We stand now at the edge of human imagination, staring into the abyss of light speed and time itself. Already, relativity has revealed to us that the faster we move, the slower our clocks tick. Already, black holes have shown us places in the cosmos where time itself can all but stop. But still, the question lingers like a ghost. What happens if you reach the speed of light? To answer, we must not only look backward to history, not only to Einstein, but also forward, into the strange future of physics, where theories wrestle with paradox and possibility. This is the realm of the impossible, and yet it is here that the human spirit thrives. Einstein's legacy and the human struggle with time. Einstein's theory did not only transform physics, it transformed our philosophy of existence. Before him, time was the same everywhere, a universal ticking metronome that no one could escape. After him, time became relative, personal, a rhythm that bends and stretches. But even Einstein's triumph left questions unanswered. His equations described the cosmos beautifully, yet they did not explain everything. For at the quantum scale, the realm of atoms, particles, and probabilities, time behaves in strange and unpredictable ways. In quantum mechanics, particles can appear to move backward in time in certain interpretations. Virtual particles flicker in and out of existence in an instant, as if borrowing time itself. And though these effects obey strict laws, they hint at a deeper mystery. Perhaps time is not what we think it is. Perhaps it is not fundamental, but emergent, like a shadow of something deeper.
Step away from equations for a moment and consider the human heart. We feel time not in physics, but in memory, in longing, in regret. To ask whether time stops at the speed of light is not only to ask about photons, it is to ask about ourselves. Could we ever escape the grip of aging, the relentless march of seconds? Could we ever step outside the story of our own lives? We dream of freezing moments, of holding on to a kiss, a sunset, a final goodbye. We dream of immortality, of youth eternal. And in these dreams, light speed becomes more than science. It becomes symbol, a metaphor for eternity, for the stillness we long for but cannot reach. But perhaps we should be careful, for without time, without change, without endings, would life still have meaning? A symphony with no final note is not music. A story with no end is not a story. Perhaps the tragedy of time is also its gift. The event horizon of human knowledge. As we push deeper into this mystery, we confront our own limits. Relativity has taken us far. Quantum mechanics has taken us further. But together they clash. To understand what truly happens at the speed of light, we may need a new theory entirely, a theory of everything. String theory, loop quantum gravity, holographic principles. These are attempts to unify the laws of the cosmos. Some suggest the universe is a hologram, where time itself emerges from deeper entanglements. Others propose that black holes hold the secret, their paradoxes hinting at truths beyond Einstein. But until we find this final theory, the question remains partly open. Physics gives us equations, philosophy gives us meaning. Together, they point us toward an answer both awe-inspiring and humbling, that light speed is not merely a velocity, but the edge of reality itself. So, let us return to the question one final time. Does time stop when you hit the speed of light? For us, beings of mass, bound to clocks and heartbeat, the answer is no. We can never reach light speed. We can approach it, feeling time slow, but never halt. For light alone, the answer is stranger. Photons do not experience time at all. For them, emission and absorption are one and the same. They are timeless. And for us, gazing upward, that truth is both alien and beautiful. Every ray of sunlight on your face is a fragment of eternity. Every star you see is a message sent across billions of years, yet delivered in an instant to the photon itself. In that light, you are connected to the birth of galaxies, to the first fires of creation, to the story of the cosmos itself. Perhaps the true answer is not about whether time stops, but about what time means. For time is not a prison, but a path. It is the canvas upon which our lives are painted. To escape it would be to erase the painting itself. So we remain travelers, never reaching light speed, always bound to the river of seconds. But in that river, we find meaning, we find love, we find story. And when we look at the light of the stars, we are reminded that beyond us lies a mystery we may never fully grasp, but one that will forever call us to wonder. Time, light, eternity, the three great mysteries, bound together. And in their dance, the story of everything. The story of light, and with it the very structure of time, is not merely a tale of physics, it is a grand chronicle of human civilization. By the dawn of the 20th century, humanity stood on the shoulders of centuries of thinkers: Aristotle, Galileo, Newton, Maxwell. But it was Albert Einstein who transformed the conversation forever, declaring with bold certainty that the speed of light was not only the fastest velocity in the universe, but the fundamental limit, the ultimate speed limit of reality itself. For millennia, time had been assumed to be universal, ticking forward identically for all observers. The pendulum swung the same way whether in Rome or in Beijing, whether in 500 BCE or in the heart of the Industrial Revolution. The human imagination believed in time as absolute, an unshakable stage upon which events unfolded. But Einstein's revelation shattered this certainty. Time, he revealed, was relative. And what gave it relativity? Light. Light, moving through the void at 299,792 kilometers per second, was not just a beam, not just a wave, not just a particle. It was the ruler of the cosmos, the standard by which all events, all distances, and all clocks must be measured. If you approach the speed of light, your time would stretch, your mass would swell, your energy demands would rise toward infinity. At the speed of light itself, time as we know it would stop. But how did this idea, once laughed at as Einstein's folly, become the foundation of the modern scientific world? To answer, we must walk through the century that followed, a century in which humanity would repeatedly test light, chase its limits, and find both inspiration and frustration in its unreachable boundary. The early century, testing Einstein. In 1919, the first test came. During a total solar eclipse, Sir Arthur Eddington led expeditions to measure whether starlight bent around the sun, as Einstein's theory predicted. The newspapers declared revolution in science, new theory of the universe. Einstein awoke one morning to find himself a global celebrity. But fame aside, this was only the beginning. In laboratories across the world, from Cambridge to Berlin to Princeton, physicists began designing experiments to verify the strange, almost unbelievable claims of relativity. Time dilation, length contraction, mass-energy equivalence. These were not just curiosities, they were radical rewritings of the laws that had governed science since Isaac Newton. And as each decade passed, the evidence only grew stronger. The atomic age. E equals mc squared made real. If there was ever a moment when Einstein's theories became not just intellectual exercises but matters of history itself, it was during the Second World War. The equation E equals mc squared, first scribbled in 1905, was no longer a curiosity of mathematics. It became the foundation of nuclear energy and of nuclear weapons. When the atom was split in the Manhattan Project, and when humanity witnessed the blinding white light above Hiroshima and Nagasaki, the world realized the terrifying power of mass energy equivalence. A tiny fragment of matter, when unleashed, could produce the fire of stars. This was not merely science, it was history, it was politics, it was human destiny. Light and energy, bound by Einstein's equation, had entered the bloodstream of civilization. And yet in that same moment of terror, relativity also promised a future. Perhaps a future where the immense energies of the universe could be harnessed not for destruction, but for propulsion, for exploration, for voyages to the stars. The space age, time in orbit. The Cold War fueled rockets into the sky, but it also brought relativity back into focus. For when Yuri Gagarin orbited Earth and when Neil Armstrong stepped onto the lunar soil, time itself became part of the mission. Clocks aboard satellites ticked differently than those on Earth. At first, the differences were small, measured in nanoseconds, but they were undeniable. The faster you moved, the slower your time. The higher you climbed in Earth's gravity well, the faster your time compared to those below. Relativity was not just theory, it was engineering. By the late 20th century, the GPS satellites orbiting Earth had to include relativity in their calculations. Without Einstein's corrections, your smartphone would place you miles away from your true location. Relativity was not just an abstract law of the cosmos, it was woven into the fabric of daily human life. The speed of light remained untouchable, but its fingerprints were everywhere. The particle accelerators, chasing the limit.
But what about actually reaching it? Could anything with mass ever approach the sacred barrier? In the underground tunnels of particle accelerators, from Fermilab to CERN's Large Hadron Collider, humanity created the fastest machines ever built. Protons and electrons were whipped around circular tracks until they were traveling at 99.999999% the speed of light. And what happened? Their lifetimes stretched. A particle that might normally exist for a fraction of a second could endure hundreds of times longer, its clock slowed by the sheer velocity of its flight. Time dilation, written on chalkboards in lecture halls, now appeared as real as sparks in the detectors. But there was always a wall. For every increase in speed, the energy demands skyrocketed. To push a single particle even closer to light speed required colossal machines, immense electrical power, and entire international collaborations. The universe was repeating its law. You may approach the boundary, but you will never cross it. The human question. Could we ever? And yet the question burns in us. Could a human being ever ride that edge? Could a spacecraft one day cruise at near-light velocities, stretching time so that decades on Earth passed like days for those aboard? The concept of time dilation makes interstellar travel possible in principle. A journey to Proxima Centauri, our nearest stellar neighbor, might take 4 years at light speed. For the traveler moving near light speed, the journey might feel even shorter, but for Earth, decades or centuries could pass. Science fiction has often played with this paradox. A traveler departs, only to return to find their world aged beyond recognition, their family long gone, their civilization transformed. This is no fantasy. It is the unavoidable consequence of Einstein's equations. To ride the edge of light is to step outside of ordinary human time. to gamble with history itself. Black holes and horizons. But perhaps the most dramatic stage on which relativity plays out is not in accelerators or rockets, but in the cosmos itself. Near a black hole, light bends and time slows. The event horizon, the boundary from which not even light can escape, represents the ultimate edge. To an outside observer, a traveler falling toward the horizon appears to freeze, their time grinding to a halt. But for the traveler themselves, time continues. They fall inward, while the universe beyond rushes forward. It is a cosmic metaphor for light's dominion. Where light stops, time stops. And here lies the strange poetry of Einstein's vision. The same laws that forbid us from breaking light speed also weave together the stars, the galaxies, the black holes, and the fate of the universe itself. The quantum frontier. But the 20th century did not belong to relativity alone. Alongside Einstein's great edifice rose the equally strange revolution of quantum mechanics, and at the heart of both theories was light. Photons, the quanta of light, behaved as both particles and waves, interfering with themselves, tunneling through barriers, and tangling across distances. They traveled at light speed because they had no rest mass. For them, time did not exist. From the perspective of a photon, the universe is instantaneous, birth and arrival collapsing into a single act. And so the paradox deepens. Time does not stop for us, but it does stop for light. Light is eternal motion frozen outside of time, the messenger that carries the universe's story from one moment to another. The 21st century. Beyond Einstein? Now, in the new millennium, physicists continue to probe. Experiments at CERN, the search for gravitational waves, the study of cosmic background radiation all reaffirm Einstein's vision, but also hint at mysteries still unsolved. Could there be particles that travel faster than light? Tachyons, theoretical ghosts of equations? Could wormholes, predicted by general relativity, offer shortcuts that bypass the speed limit? Could quantum entanglement, where particles influence each other instantaneously across vast distances, reveal a deeper layer of reality in which light is not the ultimate measure?
These questions remain open, but one truth remains solid. In every experiment, in every observation, light remains the boundary. No ship has pierced it, no particle has crossed it. It is not merely a law of physics, it is the edge of history. The legacy of a century. So, does time stop when you hit the speed of light? The historical answer, tested through eclipses, bombs, rockets, satellites, and colliders, is no. For us, time never stops. We may approach, we may slow, but only light itself inhabits that timeless realm. For humanity, the pursuit of this question has defined an entire century of science. It has given us the bomb and the satellite, the collider and the GPS, the black hole and the Hubble telescope. It has rewritten our place in the cosmos, and it continues to drive our search for knowledge. The speed of light is not just a number, it is a destiny. And, perhaps in some future century, when our descendants look back on this era, they will say that this was the age when humanity first glimpsed the true stage of the universe, not a fixed arena, but a dance of time and light, forever intertwined. The quest is unfinished, the boundary remains, and so long as it does, we will continue to chase it, across laboratories, across skies, across galaxies. Because the question is not only scientific, it is human. We do not ask whether time stops at light speed merely to fill equations.
We ask it because it speaks to the deepest longing of our species, the desire to escape limits, to outrun mortality, to find a place beyond time. And in that pursuit, as in all pursuits of science, we discover not only the universe, but ourselves. Time, humanity's oldest riddle, and the speed of light, its most elusive key. For more than a century, Einstein's theory of relativity has reigned supreme, declaring with bold finality, nothing can move faster than light. Yet history shows us that every time humankind has faced an impossible, someone has dared to push against it. And so the question still burns in laboratories, universities, and even the corridors of power. What lies beyond the light barrier? To understand this race, we must first step back to the crucible of the 20th century, a century defined not only by wars and revolutions, but by a scientific transformation so radical it rewrote our relationship with time itself. When Einstein published his special theory of relativity in 1905, the world was still fueled by coal, steam, and empire. The Wright brothers had barely lifted an airplane off the ground. The idea that clocks could slow down, that time could bend under motion, seemed less like science and more like philosophy. Yet within decades, the brutal march of history would turn Einstein's strange mathematics into tools of survival and domination. The Cold War and the cosmic race. After the Second World War, two superpowers emerged, America and the Soviet Union. Their rivalry reached across oceans and continents, and inevitably into the stars. The space race was not merely about planting flags on the moon. It was a stage for physics itself, a living laboratory for relativity. Every rocket launched was not just a weapon of prestige, but a test of Einstein's equations. Sputnik in 1957, Yuri Gagarin's orbital flight in 1961, Apollo 11's lunar landing in 1969. Each milestone pushed humankind further from Earth's cradle. Yet behind the drama of astronauts and cosmonauts, physicists quietly wrestled with relativity's implications. Satellites moving at thousands of miles per hour experienced time differently. Their onboard clocks drifted ever so slightly compared to clocks on Earth. For generals and politicians, this meant better missiles. For scientists, it meant Einstein was right. Time really did dilate. The Cold War made relativity practical. When America built the global positioning system, satellites had to account for both special relativity, time moving slower at high speed, and general relativity, time moving faster in weaker gravity above Earth. Without these corrections, GPS would be off by miles within a single day. Einstein was no longer theory, he was infrastructure. The particle accelerators, Earth's light-speed laboratories. But rockets and satellites could only travel so fast. If humanity wanted to truly approach the speed of light, it would need a different kind of tool. Enter the particle accelerator. In vast underground tunnels, physicists built machines to hurl protons and electrons at near-light speeds. The first accelerators were modest, simple rings a few meters across. But as the decades passed, they grew into behemoths. Fermilab in Illinois, CERN's Large Hadron Collider beneath the French-Swiss border. These machines became the world's fastest racetracks, where subatomic particles danced on the razor's edge of light speed. And what did we learn? That as particles approached light speed, their masses effectively increased. Pushing them faster required exponentially more energy, exactly as Einstein had predicted. The barrier held firm. No matter how much power scientists poured into the machine, the speed of light refused to be breached. But in the process, accelerators gave us gifts beyond measure. They revealed the Higgs boson, the God particle, the keystone of the standard model of physics. They showed us that the vacuum of space is not empty, but alive with quantum fields. And in every experiment, time itself bent under speed, proving relativity again and again. Quantum entanglement, the silent challenger. Yet as particle physicists celebrated Einstein's victories, another branch of science whispered a challenge. Quantum mechanics, born in the same era as relativity, described a universe where particles could exist in multiple states at once, where uncertainty ruled, and where entanglement allowed particles separated by light years to communicate instantly. Einstein himself distrusted this strangeness, dismissing it as spooky action at a distance. For him, the speed of light was sacred, the ultimate speed limit. Yet modern experiments have shown entanglement to be real. Two particles, when linked, can affect one another faster than light could travel between them. Does this break relativity? Not exactly. The information exchange cannot yet be harnessed to send messages faster than light, but the mere existence of entanglement hints that perhaps, beyond the veil of our current understanding, the cosmos allows loopholes. Atomic clocks and the march of proof. If quantum entanglement hints at mysteries, atomic clocks hammer down certainty. In 1971, physicists Joseph Hayfel and Richard Keating placed atomic clocks aboard commercial airliners. They flew around the world, eastward and westward, while reference clocks ticked quietly in laboratories. When the planes landed, the results stunned even the most skeptical. The airborne clocks had shifted, tiny fractions of a second, but measurable, undeniable. Relativity had predicted it. The faster you move, the slower your time. Since then, the experiment has been repeated countless times, with satellites, jets, and even mountain peaks. Today's most precise clocks, ticking with laser precision, can detect relativistic effects from standing just a few centimeters higher on a table. Time, once absolute, is now fragile, elastic, subject to the slightest shift in speed or gravity. History's echo, from Galileo to Einstein to us. It is tempting to see relativity as a modern story, but it is part of a much older saga. In the 1600s, Galileo dared to suggest that motion was relative, that the laws of physics should be the same whether on a ship or on a shore. In the 1800s, James Clerk Maxwell revealed that light itself was an electromagnetic wave, traveling at a fixed speed regardless of the observer. These stepping stones led to Einstein, who united space and time into a symbol fabric and crowned the speed of light as its unbreakable law. Now, in the 21st century, we live within the legacy of this history. Every phone in your pocket, every GPS satellite orbiting Earth, every medical scan in a hospital, all whisper Einstein's truth. And yet, as history has shown us, no truth remains unchallenged forever. The human dream. What if?
What if one day we find a way around the light barrier, not by brute force, but by bending the rules? Wormholes, warp drives, quantum tricks. Today they are theory. Tomorrow they may be blueprints. Every great leap in history once lived in the realm of impossibility. To break the light barrier would be more than science. It would be history's most profound revolution. Not just new empires or new technologies, but new eras of human existence. Colonies around other stars, communication across galaxies, a civilization not bound by centuries of waiting for light to travel, but linked across the cosmos in real time. This dream haunts scientists, fuels science fiction, and inspires new generations to enter laboratories. It may take decades, it may take centuries, or it may never come at all. But as history proves, humanity is never content with limits. Conclusion: the race goes on. And so the race beyond Einstein continues. The speed of light remains unbeaten, its throne unshaken. But the story is far from over. From Galileo to Newton, from Maxwell to Einstein, from the Cold War to CERN, the pursuit of speed has been the heartbeat of science itself. Perhaps the light barrier is eternal. Or perhaps one day, in some hidden corner of physics, humanity will discover the path beyond. Until then, we live in Einstein's universe, a universe where time slows, where clocks tick differently in the sky than on the ground, and where the dream of breaking light speed pushes us ever forward. The race is not just about science. It is about us. Our hunger to know, our refusal to stop, our history, written not just in books and battles, but in the ticking of time itself. And as long as that hunger remains, the question will endure. Does time stop when you hit the speed of light? For now, the answer is no. But the pursuit of that mystery may never stop. Close your eyes for a moment and imagine this. You're standing at the edge of a diving board, high above a crystalline pool. The water below catches fragments of sunlight, creating a mosaic of light and shadow that dances endlessly. Your toes curl around the edge of the board. Your heart beats once, twice, and then you leap. In that suspended moment between board and water, between intention and impact, something magical happens. The world seems to slow. Your mind captures every detail with impossible clarity. The way the air feels against your skin, the distant sound of laughter from the poolside, and the approaching surface of the water that will soon embrace you. And then, in that infinitesimal moment before you hit the water, time seems to stop. This isn't just your imagination. This is one of humanity's most profound questions, wrapped in the mystery of physics, consciousness, and the very nature of reality itself. Tonight, we're going to embark on a journey through time, quite literally, to explore whether time truly stops when you hit something, or if something far more beautiful and complex is happening in those crucial moments of impact. Our story begins not with modern physics, but with a dreamer who lived over 2,000 years ago, walking the marble steps of ancient Greece, pondering questions that would echo through millennia. The Paradox Whisperer. Ancient Greece, 5th century BCE. The Mediterranean sun cast long shadows across the agora as Zeno of Aelia walked slowly through the marketplace, his sandals creating a gentle rhythm against the worn stone. Merchants called out their wares, fresh olives, bronze tools, scrolls of poetry, but Zeno's mind was elsewhere, lost in a puzzle that would torment and inspire thinkers for over 2 millennia. Picture this ancient philosopher, his beard gray with wisdom, his eyes bright with curiosity. He stops suddenly in the middle of the bustling square, causing a young merchant to nearly stumble into him with an armload of pottery. But Zeno doesn't notice. His attention is fixed on something far more extraordinary than earthenware. He's watching a simpy arrow fly through the air. "Forgive me," he murmurs to his student, Aristotle's grandfather among the listeners, "but I've just realized something impossible." The arrow, shot by a young archer practicing his craft, arcs gracefully through the afternoon air toward a distant target. To everyone watching, it's the most natural thing in the world. The arrow flies, it hits the target, the crowd cheers. Simple. But in Zeno's brilliant mind, something far more mysterious is unfolding. "Consider this," Zeno says, his voice carrying the weight of revelation. "For the arrow to reach its target, it must first travel half the distance. And before it can travel that half, it must travel half of that, a quarter of the total distance. And before the quarter, half of that, an eighth." His student furrows his brow. The crowd continues its busy chatter, unaware that they're witnessing the birth of one of philosophy's greatest puzzles. Zeno continues, his voice growing more intense with each word. "But don't you see, this division never ends.
Half of a half of a half infinitely. If the arrow must complete an infinite number of tasks before reaching its target, and each task takes some amount of time, however small, then the arrow should never reach its destination at all. Yet here it flies, and there it strikes its mark. The student's eyes widen as the implications sink in. Master, are you saying that all motion is impossible? Zeno smiles, that enigmatic smile of a philosopher who has just opened a door to mystery rather than closed it. He's saying that what we think we understand about movement, about time, about the very moment when moving things meet stationary things, might be far more complex than our senses tell us. He gestures toward the target, where the arrow now quivers, embedded in the straw. In the moment that arrow hit its mark, did time stop? Or did something else happen, something so strange and wonderful that we're only now beginning to ask the right questions?
The Lightning Catcher, Switzerland, 1905. In a cramped patent office in Bern, Switzerland, a young man with unruly hair and penetrating eyes sits at his desk, supposedly reviewing applications for new inventions. But Albert Einstein's mind is elsewhere, traveling at impossible speeds through thought experiments that will reshape humanity's understanding of space, time, and the very nature of reality. It's a quiet afternoon in spring, and Einstein finds himself distracted by the most ordinary of sights, a tram rumbling down the cobblestone street outside his window. As he watches passengers boarding and alighting, a question begins to form in his mind, a question that connects directly to our ancient puzzles about time and impact. Picture Einstein in this moment, 26 years old, still unknown to the world, his desk cluttered with patent applications and his own secret calculations. He picks up his pen, not to review another inventor's work, but to chase down an idea that's been haunting him. "What if," he murmurs to himself, "I were traveling on a beam of light?" This isn't just daydreaming, this is the birth of special relativity, and it begins with Einstein imagining impacts of a very different kind. As he sits there, watching the tram disappear around a corner, he envisions himself moving at the speed of light, looking back at a clock tower in the city center. The revelation hits him like a physical blow. If he were traveling at the speed of light, moving away from the clock, the light carrying the image of the clock's face could never catch up to him. Time, as measured by that clock, would appear to stand still. "Mein Gott," he whispers, his hand trembling slightly as he writes, "time is not absolute. It's relative." But Einstein's breakthrough goes even deeper than this. As he develops his equations over the coming months, he realizes something profound about the moment of impact, any impact, from the collision of cosmic bodies to the simple act of a hammer striking a nail. Imagine sitting beside Einstein as he works through these revolutionary ideas. His apartment is modest, his wife Mileva occasionally bringing him tea as he fills page after page with calculations. But what he's discovering will change everything we thought we knew about those crucial moments when motion meets resistance and transforms. "Listen," Einstein tells his friend Michele Besso during one of their evening walks along the Aar River. "When two objects collide, let's say two trains approaching each other, what we think of as the simultaneous moment of impact isn't actually simultaneous at all." Besso looks puzzled. How can a collision not be simultaneous? Either they hit or they don't. Einstein stops walking, picks up a stone, and tosses it into the river. They watch the ripples spread outward in concentric circles. The moment that stone hit the water, when exactly did that happen? From our perspective here on the bank, it happened at one specific instant. But imagine observers at different distances, traveling at different speeds. To each of them, the moment of impact would appear to occur at slightly different times. "But that's impossible," Besso protests. "No," Einstein says, his eyes bright with the thrill of discovery.
That's relativity. Time isn't a constant backdrop against which events occur. Time is woven into the very fabric of space-time, and that fabric can stretch, compress, and bend depending on motion and gravity. As they continue their walk, Einstein explains what this means for our question about time stopping at impact. In moments of high-energy collision, when objects moving at tremendous speed strike each other, time doesn't stop, but it does something far more interesting. It dilates. It stretches like taffy. He pauses to watch a train crossing a distant bridge. If you were on that train, moving at speeds approaching the speed of light, and you threw a ball against the wall of your compartment, the impact would seem perfectly normal to you. The ball would bounce back, time would flow normally. But to someone standing still beside the tracks, watching your train flash by, that entire sequence would appear to unfold in slow motion. The collision between ball and wall would seem to take much longer. This is Einstein's gift to our ancient question, the realization that time doesn't simply stop or flow, it's flexible, malleable, intimately connected to motion and energy. In moments of impact, especially high-energy impacts, time reveals its true nature as something far more complex and beautiful than our everyday experience suggests. But Einstein's insights go even deeper. As he develops his general theory of relativity over the next decade, he'll realize that gravity itself is the curvature of space-time, and that massive collisions, the impact of neutron stars, the collision of galaxies, don't just affect time locally, but send ripples through the fabric of space-time itself. Every collision, Einstein will later write, is a conversation between matter, energy, space, and time. In the moment of impact, these fundamental aspects of reality dance together, creating brief symphonies of physics that we're only beginning to learn how to hear. As our evening walk with Einstein and Besso comes to an end, the young patent clerk looks up at the stars beginning to appear in the darkening sky. Somewhere out there, he says softly, cosmic impacts are occurring that stretch and compress time in ways we can barely imagine. Black holes colliding, releasing gravitational waves that carry the memory of those impacts across billions of years. The universe is full of moments when time doesn't stop, but transforms. Einstein couldn't know that his equations would one day allow us to detect these gravitational waves, to literally listen to the sound of cosmic impacts occurring billions of years ago. He couldn't know that his insights about time dilation would become essential for technologies like GPS satellites, which must account for the fact that time flows slightly differently at different altitudes and speeds. But on this quiet evening in Bern, as he makes his way home to continue his calculations, Einstein carries with him the seed of a revolutionary understanding that the question, "Does time stop when you hit something?" is really asking about the fundamental nature of reality itself, about the dance between matter and space-time that plays out in every collision, every impact, every moment when the moving world meets resistance and transforms.
The Quantum Dancers. Copenhagen, Denmark, 1927. The winter snow falls gently outside the windows of the Institute for Theoretical Physics, where a group of brilliant minds has gathered to grapple with mysteries that make even Einstein's relativity seem straightforward. Inside the warm, book-lined conference room, Niels Bohr paces thoughtfully while Werner Heisenberg scribbles equations on a blackboard covered with symbols that would look like magic to earlier generations. They are wrestling with the quantum world, the bizarre realm of atoms and particles, where the very act of observation changes what is observed, where particles can be in multiple places at once, and where the concept of hitting something takes on meanings that would have astonished Zeno, Galileo, and even Einstein. Picture Heisenberg, barely 25 years old, his face intense with concentration, as he contemplates a simple question that has emerged from their quantum investigations. What happens in the moment when a particle hits another particle? The problem, Heisenberg says to the assembled physicists, is that we cannot speak of the moment of impact in the classical sense. At the quantum level, there is no precise moment when two particles collide.
Instead, there are probability waves, interactions that unfold over time in ways that defy our everyday understanding. Bohr nods thoughtfully, his pipe creating small clouds of aromatic smoke. He says, "Consider an electron approaching an atom. In classical physics, we would say the electron either hits the atom or misses it. But in quantum mechanics, the electron exists in what we call a superposition. It simultaneously hits and misses until the moment we observe the result." To understand what they're discovering, imagine shrinking down to the subatomic level, becoming small enough to witness the dance of particles and waves. Here, in this quantum realm, our question about time stopping takes on an entirely new dimension. When particles interact at the quantum level, they don't collide like billiard balls on a table. Instead, they exist as probability clouds, wave functions that describe not where they are, but where they might be. When two such clouds meet, they don't hit each other in any conventional sense. They interfere, overlap, create new patterns of possibility. Time at this level, explains Max Born, another member of this revolutionary group, is not the steady tick of a clock. It's quantized, divided into the smallest possible units, what we call Planck time. Each quantum of time is so brief that in a single second, there are more Planck time intervals than there are seconds that have passed since the beginning of the universe. The implications are staggering. In the quantum world, the moment of impact isn't a moment at all. It's a process that unfolds across many quantum time intervals. During these intervals, particles exist in states that classical physics would consider impossible. They tunnel through barriers they shouldn't be able to cross. They exist in multiple locations simultaneously. They remain entangled across vast distances, influencing each other instantaneously. Heisenberg stands at the blackboard, his uncertainty principle written in chalk behind him, delta x times delta p equals h bar over 2. This tells us something profound about the nature of collision. We cannot simultaneously know exactly where a particle is and exactly how fast it's moving. The more precisely we try to pinpoint the moment and location of impact, the less we can know about the momentum and energy involved. So in a sense, adds Wolfgang Pauli from the back of the room, time doesn't stop during quantum collisions because time at this level is already broken up into discrete, indivisible chunks. Each quantum interaction takes place over multiple quantum time intervals, but each quantum of time is so brief that the concept of stopping becomes meaningless. As the afternoon progresses, these brilliant minds piece together a picture of reality that is both more strange and more beautiful than anyone had imagined. At the quantum level, particles don't simply hit each other, they dance together in choreographed interactions governed by probability and uncertainty. Think of it this way, Bohr settles into his chair with his pipe. When you ask whether time stops when you hit something, you're assuming that hitting is a simple, instantaneous event. But we now know that every collision, no matter how simple it appears, is actually composed of countless quantum interactions, each unfolding according to the laws of probability rather than certainty. The conversation continues into the evening, with these physicists gradually realizing that their discoveries about quantum mechanics connect back to the ancient philosophical questions posed by Zeno. The paradox of the arrow, they realized, wasn't just a logical puzzle, it was an intuitive glimpse into the quantum nature of reality, where motion and time are far more complex than our everyday experience suggests. Perhaps, Heisenberg muses as the session winds down, the question isn't whether time stops when you hit something, but whether we can ever truly understand what hitting means at the deepest levels of reality. Every collision is a quantum symphony, with particles and waves dancing together in patterns of probability that unfold across multiple scales of time. Outside, the snow continues to fall, each flake following its own unique path through the air before landing softly on the cobblestones of Copenhagen. Each landing is, in its own way, a collision, a moment when a complex ice crystal moving through space meets the solid Earth. But now we know that this simple event involves countless quantum interactions, probability waves collapsing into actuality, energy transferring between molecular structures in ways that would have seemed like magic to earlier generations. As the physicists gather their papers and prepare to leave, they carry with them a new understanding that the moment of impact, whether it's a snowflake hitting the ground or particles colliding in the heart of a star, is not a single instant, but a complex process unfolding across the quantum structure of space and time itself. The question, does time stop when you hit something, has evolved into something far more profound. How does time behave at the intersection of the quantum and classical worlds? And what does this tell us about the fundamental nature of reality?
The Cosmic Clock Keeper. Princeton, New Jersey, 1955. Einstein sits in his study at the Institute for Advanced Study, his hair now completely white, his eyes holding the wisdom of decades spent contemplating the deepest mysteries of the universe. At 76, he is still working, still wondering, still pushing at the boundaries of human understanding. On his desk lies a letter from a friend whose wife has recently died, and Einstein is composing a response that will become one of the most beautiful statements ever made about the nature of time. For us believing physicists, he writes, the distinction between past, present, and future is only a stubbornly persistent illusion. As he pauses in his writing, Einstein's mind drifts to a question that has haunted him throughout his career, a question that connects the intimate human experience of time with the vast cosmic clockwork he has spent his life trying to understand. What happens to time in those moments when things collide, when the orderly flow of existence meets sudden, dramatic change? Outside his window, Princeton is quiet in the afternoon sun. Students walk slowly across the campus, occasionally stopping to speak with friends before continuing on their way. To an observer, time seems to flow steadily, uniformly. But Einstein knows better. His equations have revealed that time is far more flexible, more mysterious than our everyday experience suggests. Picture Einstein in this moment of reflection, surrounded by the accumulated wisdom of a lifetime spent peering into the fundamental nature of reality. His special and general theories of relativity have revolutionized our understanding of space and time, but they have also raised new questions about what happens in those crucial moments when motion meets resistance, when change occurs, when one thing impacts another. The truth, Einstein murmurs to himself as he returns to his letter, is that every moment of impact, from the collision of galaxies to the contact between pen and paper as I write these words, reveals something profound about the nature of time itself. Over the course of his career, Einstein has come to understand that massive objects literally warp the fabric of space-time around them. Near a black hole, time slows dramatically compared to time in empty space. During the collision of neutron stars, the gravitational effects are so intense that time dilation becomes extreme. Seconds near the impact stretch into minutes as measured by distant observers. But there's something even more beautiful in Einstein's vision of cosmic impacts, the realization that every collision sends ripples through space-time itself. When massive objects accelerate toward each other and collide, they create gravitational waves, distortions in the fabric of space-time that travel outward at the speed of light, carrying information about the impact across the cosmos. Imagine, Einstein writes in his notebook, setting aside the condolence letter for a moment, two black holes spiraling toward each other across billions of years. As they draw closer, they accelerate, warping space-time ever more dramatically. Time near them slows compared to time elsewhere in the universe. And in the final moment of collision, when these massive objects merge, they release more energy in gravitational waves than all the stars in the observable universe emit in light. Einstein's equations predict these gravitational waves, though he doubts they will ever be detected directly. The distortions they create in space and time are incredibly tiny, smaller than 1,000th the width of a proton. But he understands that these waves carry within them the memory of cosmic impacts, preserving the story of what happens to time in moments of the most extreme collisions in the universe. In that final moment, when the black holes merge, time doesn't stop, it transforms. The collision creates a new black hole, a new curvature of space-time, a new relationship between matter and the geometry of the universe itself. Time reshapes itself around that new reality. As the afternoon light slants through his study window, Einstein contemplates the philosophical implications of his discoveries. If time is truly relative,
If it can stretch and compress based on motion and gravity, then the question, does time stop when you hit something, depends entirely on perspective, on where you are, how fast you're moving, and how strong the gravitational fields around you happen to be. For the person experiencing the impact, time flows normally. They feel the collision, experience the change, live through the transformation at what seems like the ordinary pace of existence. But for observers at different distances, moving at different speeds, existing in different gravitational environments, that same impact unfolds at different rates, creates different distortions in the flow of time.
Einstein stands and walks to his window, looking out at the peaceful campus scene. A group of students is playing catch with a ball, and each time the ball is caught or thrown, Einstein sees a miniature example of the cosmic principles he has spent his life exploring. The ball follows curved paths through space-time, its motion creating infinitesimal gravitational effects, its impact with each player's hand representing a moment when kinetic energy transforms into other forms: heat, sound, molecular vibrations. Even here, he thinks, in this simple game, time is revealing its flexible nature. The moment of catch, of impact between ball and hand, creates brief changes in the local gravitational field, tiny accelerations that cause time to flow at infinitesimally different rates. Returning to his desk, Einstein completes his letter about the illusory nature of time's divisions, but his mind continues to work on the deeper question. Throughout his career, he has shown that time is not a steady river flowing from past to future, but rather a dimension woven together with space, creating a fabric that can bend, stretch, and ripple in response to matter and energy. In moments of impact, whether cosmic collisions or everyday encounters, this flexible nature of time becomes most apparent. Time doesn't stop. It dances, responding to the energy and motion involved in each collision, creating patterns of temporal distortion that ripple outward through the universe, carrying information about what happened in those crucial moments when one thing meets another. As the sun sets over Princeton, Einstein finishes his correspondence and turns to his ongoing work on unified field theory, his attempt to weave together all the forces of nature into a single elegant description. But the question about time and impact remains with him, a thread connecting his scientific discoveries to the deepest human experiences of change, collision, and transformation. The cosmic clockkeeper, as history will remember him, has shown us that time itself is perhaps the most dynamic participant in every moment of impact, every collision, every instant when the universe reshapes itself and time reshapes along with it. The Wave Hunters, Hanford, Washington, and Livingston, Louisiana, 2015. In the high desert of eastern Washington, a massive L-shaped facility stretches across the landscape like a giant ruler laid against the earth. Each arm of this instrument extends for 4 kilometers, longer than the entire campus of Princeton, where Einstein once contemplated the nature of time and impact. This is LIGO, the Laser Interferometer Gravitational Wave Observatory, and on September 14, 2015, it is about to capture something that will transform our understanding of cosmic collisions forever. Dr. Gabriela Gonzalez, a physicist from Louisiana State University, sits in the control room monitoring data streams that most people would find utterly incomprehensible. Endless scrolling numbers, wave-like patterns dancing across computer screens, the digital heartbeat of an instrument so sensitive it can detect changes in distance smaller than 1/10,000th the width of a proton. It's 4:51 a.m. local time when the computers begin to register something extraordinary. A signal unlike anything seen before appears simultaneously in both LIGO detectors, one here in Hanford, one 3,000 kilometers away in Louisiana. The pattern is unmistakable, matching exactly what Einstein's equations predicted nearly a century ago: gravitational waves created by the collision of 2 black holes.
Picture the scene in both control rooms as scientists begin to realize what they're witnessing. After decades of searching, after building instruments of impossible precision, they are detecting the ripples in space-time created by an impact so violent, so energetic, that it shook the very fabric of reality across more than 1 billion light-years. "My God," whispers Dr. Gonzalez as she examines the data. "We're not just detecting gravitational waves, we're hearing the sound of time itself being distorted by the most powerful collision in the observable universe." The story behind the signal is almost incomprehensible in its scope. Over 1 billion years ago, in a galaxy far beyond our local cosmic neighborhood, two black holes, each roughly 30 times more massive than our Sun, spiraled toward each other in an ancient dance of gravity and space-time. For millions of years, they orbited closer and closer, their immense gravitational fields creating ripples that traveled outward at the speed of light. As they approached their final collision, something remarkable happened to time itself in their vicinity. The intense gravitational field of each black hole created what physicists call time dilation. Near the black holes, time slowed dramatically compared to time in the rest of the universe. An observer near the collision would experience events at what seemed like normal speed, but to distant observers, everything near the black holes would appear to unfold in slow motion.
The Clockmaker's Dream. Renaissance Italy, 1638. 300 miles south of where Zeno once walked, in the gentle hills of Tuscany, an old man sits in a prison cell. But this is no ordinary prisoner, and his cell is filled not with despair, but with the soft scratch of quill on parchment, the quiet murmur of a mind still working, still wondering, still reaching toward truth, even as his world grows smaller around him. Galileo Galilei, now 74 years old, his once dark hair silver in the candlelight, his eyes still sharp despite decades of peering through telescopes at distant moons and planets. The Inquisition has silenced his voice about the motion of Earth around the sun, but they cannot stop his mind from wandering to other mysteries, other questions about the nature of motion and time. Tonight, confined to his villa in Arcetri, Galileo is writing what will become his final great work, Two New Sciences. And in the flickering light of his study, he's grappling with a question that connects directly to our ancient friend Zeno's puzzle: what happens to time in the moments when things collide? Imagine you're there with him, sitting quietly in a corner of his study. The walls are lined with instruments of his own making, pendulums of different lengths, inclined planes of varying angles, bronze balls polished smooth by countless experiments. On his desk, beside the manuscript, sits a simple water clock, its steady drip marking the passage of moments. "Maria," he calls softly to his daughter, who has been caring for him through his house arrest, "bring me 2 stones from the garden, one large, one small." When she returns, puzzled but obedient, Galileo holds the stones at arm's length. The ancients believed that the heavy stone would fall faster than the light one. Common sense says this must be true, but common sense, he chuckles, is often the enemy of truth. He drops both stones simultaneously. They strike the floor at precisely the same moment. You see, time treats all falling objects equally. But this raises a deeper question, my dear. In the instant these stones hit the floor, what happened to time itself? Did it pause? Did it stretch? Did it remain constant while the stone's motion transformed from falling to stopping? Maria, who has grown accustomed to her father's philosophical musings, settles into a chair. "Tell me what you mean, Papa." Galileo picks up the stones, feeling their weight, their texture. "Consider this," he says.
The moment before impact, each stone possessed motion, what I call momentum. The moment after impact, that motion was gone, transferred to the floor, to the air, to heat and sound. But what about the moment of impact itself, that infinitesimal instant when motion becomes stillness? He begins to pace, his mind clearly racing. Is it truly instantaneous, this transition, or does it take some small but finite amount of time? And if it takes time, however brief, then what is happening during those moments? Is time flowing normally, or is something else occurring, some slowing, some stretching, some fundamental alteration in the fabric of temporal experience? This question haunts Galileo because he understands, perhaps better than anyone of his time, that motion and time are intimately connected. His pendulum experiments have shown him that time can be measured by motion, but also that motion unfolds within time. In the moment of impact, when motion ceases, what happens to this intimate relationship? He walks to his window, looking out at the stars that he can no longer publicly claim move around the sun. Every night, he whispers, celestial bodies move through space, occasionally meeting, sometimes colliding. Meteors strike our atmosphere and burn bright before hitting the Earth. In those moments of cosmic impact across the vast distances of space, does time maintain its steady flow, or does something more mysterious occur? Unknown to Galileo, his questions are pushing toward discoveries that won't be made for centuries. He cannot know that in the moment of impact, complex transformations occur at speeds that make his falling stones seem to move in slow motion. He cannot know about the compression waves that travel through matter at the speed of sound, creating brief moments where material properties change dramatically. He cannot know about the release of energy that temporarily increases entropy and affects the local flow of time itself. But his intuition senses something profound. "Maria," he says, returning to his chair, "I believe that in the moment of impact, time doesn't stop, it reveals its true nature. It shows us that what we think of as an instant actually contains multitudes, layers upon layers of events, each unfolding in its own time frame." He dips his quill and begins to write again. Perhaps the better question isn't whether time stops when you hit something, but whether we ever truly stop to understand what time is doing in those moments, whether we appreciate the incredible complexity hidden in what appears to be the simplest of events. As the night deepens around the villa in Arcetri, Galileo writes by candlelight, unknowingly laying groundwork for questions that future generations will explore with instruments he cannot imagine. His pendulum swings steadily in the corner, marking time, while his mind reaches forward into centuries yet to come, toward answers that will be both more beautiful and more strange than he could possibly dream. Outside his window, meteors streak across the Tuscan sky, each one a tiny example of cosmic impact, each carrying within its brief, bright moment mysteries about time and motion that humanity is only beginning to understand.
In the final moments before impact, the black holes accelerated to speeds approaching half the speed of light. The gravitational waves they created grew stronger and stronger, carrying away energy equivalent to 3 times the mass of our sun converted directly into the motion of space-time itself. Then came the collision, what scientists would later call a chirp because of the way the gravitational wave frequency increased as the black holes spiraled inward. In the last fraction of a second, as these massive objects merged, they released more energy in gravitational waves than all the stars in the observable universe emit in light at that moment. Dr. Kip Thorne, one of LIGO's founders, later described the moment.
For about 200 milliseconds, these two black holes danced around each other, sending out gravitational waves. In the final tenth of a second, they emitted 50 times more energy and gravitational waves than all the stars and galaxies in the observable universe combined were emitting in light at that moment. But here's what makes the story so profound for our question about time and impact. The collision itself lasted only milliseconds, but the gravitational waves it created have been traveling through space for over 1 billion years, carrying within them the precise signature of what happened to time in that moment of cosmic impact. As the waves passed through Earth on that September morning in 2015, they temporarily changed the length of LIGO's arms by less than the width of a proton. For just 200 milliseconds, space and time on Earth were slightly distorted by the memory of an impact that occurred when the most complex life on our planet was single-celled organisms. What we detected, explains Dr. Rainer Weiss, another LIGO pioneer, wasn't just a collision. We detected the way space-time itself responded to the most violent merger in the universe. We heard time being stretched and compressed by the impact of objects so massive that they turned space-time into something like the surface of a pond, creating ripples that spread outward at the speed of light. The LIGO detection confirmed something beautiful about Einstein's vision, that time doesn't stop during moments of impact, but instead participates in the collision as an active player. The merger of the black holes didn't just involve matter and energy. It involved the very geometry of space and time, which bent and flexed and rippled in response to the violence of the collision. In the months and years following this first detection, LIGO had registered dozens more gravitational wave events, black holes colliding, neutron stars merging, cosmic impacts so powerful they create new elements in the process. Each detection tells us something new about what happens to time in moments of extreme collision. When neutron stars merge, for example, the collision creates conditions so extreme that atomic nuclei are forged in the impact itself. Gold, platinum, uranium, many of the heaviest elements in the periodic table are created in the few seconds when these ultra-dense objects collide, and throughout this process, time dilation effects near the merger are so intense that seconds near the collision stretch into minutes as measured by distant observers. As Dr. Gonzalez reviews the data from that historic September morning, she reflects on what LIGO has revealed about our ancient question. Einstein showed us that time is relative, that it can stretch and compress, but LIGO has let us actually hear these distortions, to listen to the sound of space-time itself being shaken by cosmic impacts. We've learned that time doesn't stop during collisions, it sings. The gravitational waves detected by LIGO carry within them a kind of temporal archaeology, the precise history of how time behaved during the most violent impacts in the universe. Each wave pattern tells us about the masses of the colliding objects, their spins, their orbital dynamics, and most importantly, how their collision affected the flow of time itself in their local region of the universe. Standing in the LIGO control room as morning light begins to filter through the windows, Dr. Gonzalez and her colleagues represent the culmination of a journey that began with Zeno's ancient arrow. From philosophical paradox to mathematical theory to technological achievement, humanity has slowly learned to read the signatures of time's behavior in moments of impact. Every time we detect gravitational waves, she explains to a visiting student, we're essentially watching time behave like a fluid, rippling, flowing, carrying information across vast distances about moments of collision that occurred billions of years ago. We've learned that impact doesn't stop time, but reveals time's true nature as something dynamic, responsive, and fundamentally interconnected with space and matter.
The athlete's paradox. Tokyo Olympic Training Center, 2019. The gymnasium falls silent, except for the rhythmic thud of running feet on the track. Usain Bolt, though officially retired from competition, has come to Tokyo to work with sports scientists studying the biomechanics of human performance. At 32, his legendary speed may be behind him, but his curiosity about the physics of motion has only grown stronger. Dr. Aki Salo, a Finnish biomechanics expert, watches intently as high-speed cameras capture every millisecond of a sprinter's stride. These cameras, operating at 10,000 frames per second, reveal details of human motion that the naked eye cannot perceive. Details that bring us back to our fundamental question about time and impact. but now in the realm of human performance. "Usain," Dr. Solo calls out, "come look at this footage. I want to show you something remarkable about what happens to time during the moment your foot hits the track." On the monitor, they watch as the sprinter's foot approaches the ground in extreme slow motion. What appears to the naked eye as a single instantaneous moment of contact, foot hitting track, is revealed by the high-speed cameras to be a complex sequence of events unfolding over several milliseconds. "You see here," Dr. Salo points to the screen. "First contact occurs at the heel, but the foot doesn't stop moving. It continues to roll forward while simultaneously compressing downward. The impact creates compression waves that travel up through your leg at roughly 1,500 meters per second, faster than the speed of sound in air." Bolt leans in closer, fascinated. Throughout his career, he's felt these impacts thousands of times, but he's never seen them broken down into their component moments like this. "The interesting thing," Dr. Solo continues, "is that your brain doesn't experience this impact as a series of separate events. To your consciousness, the foot strike feels instantaneous, but in reality, it takes about 150 milliseconds from first contact to the moment your foot leaves the ground again. During that time, your body is managing forces equivalent to 3 times your body weight." This reveals something profound about human perception and the experience of time during impact. While the high-speed cameras show us the detailed, extended process of foot striking track, the athlete's nervous system processes this information in a way that creates the subjective experience of an instantaneous event. "It's like Zeno's paradox in reverse," Bolt muses. "The ancient philosopher said, motion should be impossible because of all the infinite divisions of space and time. But here we are, running, and our bodies are solving these impossible equations millions of times with every race." Dr. Yuki Tanaka, a neurophysicist working with the team, joins the conversation. "What's fascinating is how your brain handles the temporal processing of impact. When your foot hits the ground, pressure sensors in your sole send signals to your spinal cord and brain. But these signals travel at different speeds, some at 120 meters per second, others at only 1 meter per second. This means that different aspects of the same impact reach your brain at different times. The initial pressure sensation arrives first, followed by information about texture, temperature, and pain if there's any injury. Your brain somehow integrates all these temporally separated signals into a single coherent experience of hitting the ground." As they review more footage, an even more intriguing pattern emerges. The cameras reveal that elite sprinters unconsciously time their muscle activations to anticipate the moment of impact. About 50 milliseconds before the foot touches the ground, the leg muscles begin to stiffen in preparation for the collision. Your nervous system is essentially predicting the future. It's calculating exactly when impact will occur and preparing your body accordingly. In a sense, your brain is solving the same problem that physicists wrestle with, understanding the relationship between motion, time, and the moment when moving objects meet stationary ones. But there's an even deeper mystery at work in these moments of athletic impact. Research has shown that elite athletes often report experiencing time differently during peak performance, moments when time seems to slow down, when they can perceive and react to events that happen too quickly for ordinary human reflexes. "I remember races," Bolt says thoughtfully, "when everything seemed to happen in slow motion. I could see other runners' movements, feel my own foot strikes, even hear individual voices in the crowd with incredible clarity. It was like time stretched out to give me more space to exist in each moment." Dr. Tanaka nods. "We think this might be related to how your brain processes sensory information during extreme focus. When you're operating at peak performance, your nervous system seems to sample reality at a higher frequency,
like increasing the frame rate of perception. More information gets processed in the same objective time period, creating the subjective experience of time slowing down. This connects our question about time and impact to consciousness itself. During moments of athletic collision, the boxer's punch landing, the tennis racket meeting the ball, the pole vaulter's pole bending under impact, the athlete's brain enters a state where time perception becomes more finely grained, more detailed, more precise.
The moment between moments, a quiet place, present day. Let us step away from laboratories and equations for a moment, away from the rush of discovery and the excitement of measurement. Let us find ourselves in a place of perfect stillness, perhaps a garden at dawn, or a library in the late afternoon when the light slants golden through tall windows, or simply a comfortable chair where you sit now, listening to these words. Here, in this quiet space, we can reflect on the extraordinary journey we've taken together. From ancient Greece to modern research laboratories, from philosophical paradoxes to gravitational wave detectors, from quantum mechanics to virtual reality, we've been pursuing a single, beautiful question. What happens to time in moments of impact? But as we've discovered, this question isn't really about physics or neuroscience or technology. It's about something much more fundamental. It's about the nature of experience itself, about what it means to exist in time, about how consciousness encounters the world moment by moment. Think about your own life for a moment. How many impacts have shaped who you are? Not just the physical collisions, though those matter too, but the moments when one thing met another and everything changed. The first time you heard a piece of music that moved you to tears. The instant when an idea finally made sense. The moment when you realized you were in love, or when you understood that someone you cared about was gone forever. Each of these experiences was, in its own way, a collision. A moment when the moving trajectory of your life met something that changed its course. And in each case, didn't time seem to behave strangely? Didn't those crucial moments seem to last longer than they should have, contain more meaning than their duration would suggest possible? This is what we've been discovering throughout our journey, that the question, does time stop when you hit something, is really asking about the deepest mysteries of existence. It's asking how consciousness creates meaning from the flow of moments, how significance emerges from the collision between expectation and reality, how transformation occurs in the space between what was and what will be. Zeno's ancient arrow taught us that motion contains infinities, that every journey from here to there passes through countless intermediate points, each one a moment of potential impact. Galileo showed us that all objects, regardless of their weight or size, fall through time at the same rate, that time treats all things equally in their descent toward collision with the Earth. Einstein revealed that time itself is flexible, that it can stretch and compress depending on motion and gravity, that the fabric of space-time participates actively in every collision, every impact, every moment when matter and energy interact. The quantum physicist showed us that at the deepest levels, particles don't simply collide, they dance together in probability clouds, existing in multiple states simultaneously until the moment of observation collapses them into definite outcomes. LIGO's gravitational wave detectors taught us that impacts can send ripples through the very structure of reality, that collisions occurring billions of years ago still echo through the universe today, carrying information about what happened to time in those moments of cosmic violence and creation. The athletes and researchers studying human performance showed us that consciousness itself can alter temporal experience, that moments of focused impact can slow down subjective time, creating space within seconds for extraordinary awareness and precision. The virtual reality researchers demonstrated that temporal experience is far more malleable than we typically realize,
that consciousness can learn to inhabit different time streams, to experience moments of impact from perspectives that no human has ever naturally possessed. And the neuroscientists revealed the mechanisms by which our brains create the experience of time slowing down during moments of significance, showing us that temporal distortion isn't just a poetic metaphor, it's a measurable neurological reality. But what does all this mean for you, sitting quietly in this moment, considering these ideas? It means that every instant of your life is far richer, far more complex, far more mysterious than ordinary experience suggests. Right now, as you're reading these words, quantum interactions are occurring in your brain at unimaginable speeds. Gravitational waves from distant cosmic collisions are passing through your body, carrying the memory of impacts that occurred before Earth existed. Your nervous system is processing millions of sensory inputs, creating the seamless experience of existing in this moment. And if you pay careful attention, if you allow your awareness to settle into the present moment with the kind of focus that athletes and martial artists cultivate, you might notice something extraordinary happening to your experience of time. You might notice that this moment, this very instant of reading and understanding, isn't actually instantaneous at all. It has depth, dimension, layers of meaning that unfold as your attention settles more fully into the present. The words you're reading now aren't hitting your consciousness like stones hitting water, they're entering your awareness gently, creating ripples of understanding that spread outward through your mind, connecting with memories, emotions, ideas you've carried with you perhaps for years. This is what we've learned from our long investigation of time and impact, that consciousness doesn't simply receive moments, it participates in their creation. Every instant of awareness is a collaboration between your nervous system and the world around you, a dance between attention and reality that creates the experience of existing in time.
The remarkable thing, Dr. Rodriguez notes, is that all three perspectives are equally valid. Time doesn't have one correct rate of flow. It's relative, contextual, dependent on the observer and their situation. As the virtual reality session ends and they remove their headsets, both researchers reflect on what their digital explorations have revealed about our fundamental question. In the controlled environment of virtual reality, they can experience firsthand what physicists have long theorized, that time is flexible, that impact can be experienced at any temporal resolution, that the moment of collision contains infinitely rich detail when examined at the appropriate scale. Virtual reality has given us a new way to explore ancient questions, Dr. Chem concludes. Zeno's paradox, Einstein's relativity, quantum mechanics, consciousness research. We can now experience these concepts directly, rather than just thinking about them abstractly. Standing in their physical laboratory as the California sun sets outside, surrounded by the technology that allows human consciousness to experience time in new ways, they represent yet another evolution in humanity's long investigation of impact and temporal experience. The question, does time stop when you hit something, has now become, how many different ways can consciousness experience the relationship between time and impact? And what do these different perspectives reveal about the nature of reality itself? In virtual worlds where time can be controlled like a musical instrument, where impact can be experienced from any perspective, where the laws of physics become playground equipment for human curiosity, we're developing new intuitions about time, new ways of feeling our way into the deepest mysteries of existence. The Memory Keepers. Harvard Medical School, 2024. Dr. Amelia Foster adjusts the sensitivity on her neural recording equipment as her volunteer subject, a professional martial artist named James, prepares to break a wooden board with his bare hand. But this isn't just a demonstration of physical skill. It's a window into one of the most profound mysteries surrounding our question about time and impact. How does the human brain create and store memories of collisions?
And what does this tell us about the subjective experience of time? The laboratory is quiet, except for the soft humming of electronics. Electrodes attached to James's scalp will record the electrical activity of his brain in the moments before, during, and after the impact. High-speed cameras will capture the physical event at 50,000 frames per second, while the neural recordings will reveal what's happening in his consciousness during those same crucial moments. The thing people don't realize, Dr. Foster explains as she calibrates her equipment, is that your brain doesn't just passively record events as they happen. During moments of high stress or intense focus, like preparing to break a board with your hand, your nervous system goes into a heightened state that actually changes how time is processed and remembered. James stands before the wooden board, mounted securely on a frame designed for breaking demonstrations. He's done this thousands of times, but today he's participating in research that might help us understand something fundamental about consciousness and temporal experience. Ready? Dr. Foster asks. James nods, his breathing deep and controlled. As he raises his hand, the neural recording equipment begins capturing the electrical symphony of his brain preparing for impact. The strike itself happens almost too quickly to see with the naked eye. James's hand moves downward with practiced precision, strikes the board with a sharp crack, and the wood splits cleanly in half. To an observer, the entire event takes perhaps half a second. But the neural recordings tell a far more complex story. Look at this, Dr. Foster says as she reviews the data. The computer screen shows wave patterns representing different types of brain activity. About 200 milliseconds before impact, we see a massive surge in activity in the motor cortex. That's his brain preparing for the collision. But more interesting is what happens in the hippocampus and temporal lobe areas associated with memory formation.
The data shows something remarkable. In the moments surrounding impact, James's brain activity becomes extraordinarily synchronized and intense. Multiple brain regions begin working together in ways that don't happen during ordinary activities. It's as if his brain knows this moment is important and allocates extra processing power to it, Dr. Foster explains. We see increased activity in areas responsible for sensory processing, motor control, memory formation, and even emotional regulation. The impact doesn't just affect his hand, it affects his entire nervous system. When James reviews his own experience, he describes something that research subjects consistently report. The moment of impact seemed to last longer than the clock suggests it should have. As my hand approached the board, he explains, time seemed to slow down. I could feel the resistance of the air, see the grain pattern in the wood, even hear my own heartbeat. The actual impact felt like it lasted several seconds, though I know it was really just milliseconds. This temporal distortion during impact isn't unique to martial arts. Dr. Foster's research has documented similar effects in athletes, musicians, surgeons, and anyone who experiences moments of intense, focused collision or contact with their environment. What we think is happening, she explains, is that during these crucial moments, your brain samples reality at a much higher rate. Instead of the normal 10 to 15 conscious moments per second that most people experience, the nervous system might be creating 30, 40, or even 50 distinct conscious moments per second. This increased sampling rate creates more detailed memories of the impact event. When the brain later recalls the experience, it has far more information to work with than it would for a typical moment, creating the subjective impression that time slowed down. Dr. Foster shows James brain scans taken during his board-breaking demonstration. See these areas lighting up in yellow and red? That's your brain laying down what we call episodic memory traces. Detailed records not just of what happened, but of when it happened and how it felt. The implications are profound. If the brain can alter its processing rate during moments of impact, this suggests that our subjective experience of time is far more flexible than we typically realize. The question, does time stop when you hit something, becomes, how does consciousness create temporal experience, and why does it change during moments of collision?
Research in Dr. Foster's lab has revealed that different types of impact create different patterns of temporal distortion. A pianist's fingers striking piano keys, a surgeon's scalpel making an incision, a tennis player's racket meeting a ball, each creates its own unique signature of neural activity and temporal experience. Musicians are particularly interesting, Dr. Foster notes as she shows brain scans from a concert pianist. When they're performing a complex passage, their brain activity shows that they're experiencing time at multiple scales simultaneously. They're tracking the overall tempo of the piece, the rhythm of the current measure, and the precise timing of each individual note. It's like they're living in several different time streams at once. The research extends beyond individual experience to social and cultural dimensions of time and impact. Dr. Foster's team has studied martial artists from different traditions, discovering that cultural training affects how the brain processes moments of collision. A karate practitioner and a Tai Chi practitioner both break boards, but their neural patterns are very different. The karate student shows intense, focused activity during impact, very sharp, precise brain responses. The Tai Chi practitioner shows more flowing, sustained activity that begins well before impact and continues well after. Same physical event, but completely different neurological experiences of time. As evening falls over Boston, Dr. Foster reviews the day's data in her quiet laboratory. The neural recordings from James' board-breaking demonstration have revealed something beautiful about the relationship between brain, body, and temporal experience. What we're learning, she reflects, is that time isn't just something that happens to us, it's something our brains actively construct moment by moment. During impacts, collisions, moments of intense contact with the world, our nervous system has the ability to slow down subjective time, to create space within moments, to give consciousness room to fully experience what's happening. The Digital Dreamscape. Mountain View, California, 2023. In a sleek laboratory nestled in the heart of Silicon Valley, Dr. Sarah Chen adjusts her virtual reality headset and steps into a world where the laws of physics bend to human imagination. As a researcher at one of the world's leading VR companies, she's investigating how digital environments can help us understand the relationship between perception, time, and impact, our ancient question now explored through the lens of simulated reality. The virtual world around her is breathtaking in its detail, a physics laboratory where she can manipulate time itself, slowing down or speeding up the flow of moments to observe collisions at any temporal resolution she chooses. Here, in this digital realm, she can become a modern Zeno, watching arrows fly through space with perfect control over the rate at which events unfold. "Computer," she says, her voice triggering the system's AI assistant, "create a simple collision scenario, two balls approaching each other at moderate speed." Instantly, two spheres materialize in the virtual space before her, one red, one blue, each about the size of a basketball. They roll toward each other across a pristine white surface, their motion perfectly smooth, their collision inevitable. "Now slow the temporal resolution to 1000x normal speed," Dr. Chen commands. The world transforms around her. The approaching balls now move with dreamlike slowness, each revolution taking several seconds. She can walk around them, examine them from every angle, even reach out with her virtual hands to feel their surfaces as they inch toward their meeting point. This digital laboratory allows Dr. Chen to explore questions that would be impossible to investigate in the physical world. What does it mean to experience time at different rates? How does our perception of impact change when we can control the flow of temporal experience? As the balls finally meet in ultra-slow motion, Dr. Chen watches their surfaces deform, compress, and spring back. The collision that would normally last milliseconds now unfolds over minutes, revealing every detail of how kinetic energy transforms into compression, heat, sound, and rotational motion. "Fascinating," she murmurs. "In virtual reality, we can experience time the way different observers would experience it in Einstein's relativistic universe. We can slow down to quantum timescales or speed up to cosmic timescales, all while maintaining human consciousness and perception." Dr. Chen's work is part of a larger investigation into how digital environments might help us understand consciousness and time perception. Her colleague, Dr. Marcus Rodriguez, joins her in the virtual laboratory, his avatar materializing beside her just as the slow-motion collision completes. Sarah, I've been thinking about our discussion yesterday regarding subjective time experience. What if we could use VR to actually feel what time dilation would be like near a black hole? Together they design a new simulation. The virtual environment shifts around them, becoming a spacecraft approaching a massive black hole. As they draw closer to the event horizon, the simulation begins to slow down their temporal experience relative to the outside universe. According to Einstein's equations, Dr. Rodriguez explains, as they watch distant stars begin to blue shift and speed up, time near this black hole should be running much slower than time in the rest of the universe. If we were really here, a day for us might be equivalent to years for observers far from the gravitational field. In this virtual experience, they can feel something that no human has ever actually experienced: the subjective sensation of time dilation. The simulation adjusts their perception so that their own movements feel normal, but external events appear to accelerate dramatically. It's a digital approximation of what cosmic impacts might feel like to the objects involved. This is revolutionary, Dr. Chen realizes. We're not just studying time and impact intellectually anymore. We can actually experience different temporal relationships, feel what it might be like to exist in different time streams. Their research extends beyond cosmic scenarios. They create virtual environments where users can experience what it might be like to be a particle in a particle accelerator, moving at near light speeds and colliding with other particles. They simulate what it might be like to exist as a photon, experiencing the universe where time stops completely because you're moving at the speed of light. One of our most interesting discoveries, Dr. Rodriguez explains, is that when people experience these different temporal states in VR, it actually changes how they think about time in the real world. After spending an hour in a simulation where they control the flow of time, users report being more aware of temporal experience in their daily lives. As afternoon turns to evening in the physical laboratory, Dr. Chen and her team continue their exploration of digital time. They create scenarios where users can experience the world from the perspective of different creatures: a hummingbird, whose nervous system processes visual information at incredibly high rates, making the world appear to move in slow motion, or a tree, whose temporal experience unfolds over decades rather than seconds. What we're discovering, Dr. Chen explains to a visiting journalist, is that time isn't just a dimension that we move through. It's something that can be experienced in radically different ways depending on your frame of reference, your nervous system, your state of consciousness. They show the journalist a simulation where she can experience a simple collision, a ball bouncing off a wall, from multiple temporal perspectives simultaneously. In one window, she sees the collision in real time. In another, it unfolds in ultra-slow motion, revealing the complex physics of deformation and energy transfer. In a third, it's sped up dramatically, making the bounce appear almost instantaneous.
When we ask whether time stops when you hit something, we're really asking whether there's space within moments for deeper experience, for greater awareness, for the kind of presence that transforms ordinary collisions into profound encounters with reality. And the answer, as we've discovered, is beautifully complex. Time doesn't stop, but it reveals its true nature as something far more flexible, responsive, and mysterious than our everyday experience suggests. In moments of impact, whether physical, emotional, or spiritual, time opens up, creates space for transformation, allows for the kind of deep experience that can change the entire trajectory of a life. So as we near the end of our journey together, I invite you to consider this. What would it mean to live with greater awareness of time's flexibility? What would it mean to approach each day knowing that moments of impact, large and small, are opportunities for consciousness to expand, for time to reveal its hidden depths, for ordinary experience to become extraordinary? The ancient philosophers, the Renaissance scientists, the modern physicists, the contemporary researchers,
all have been pointing toward the same profound truth, that reality is far more magnificent, far more mysterious, far more responsive to consciousness than we typically realize. And you, right now, in this quiet moment of reflection, are part of this ongoing discovery. Every breath you take, every heartbeat, every instant of awareness is a moment when the moving trajectory of your consciousness encounters the world and creates something new, not just in your experience, but in the fabric of reality itself. The dance of becoming. The eternal present. As our journey draws toward its close, let us consider one final perspective on the question that has guided us through time and space, through the realms of physics and consciousness, through the laboratories of science, and the quiet chambers of reflection. We have learned that time doesn't stop when you hit something, but we have also discovered something far more beautiful, that every moment of impact is an opportunity for becoming, for transformation, for the emergence of something new from the collision between what is and what is possible. Consider the story of a raindrop falling from a cloud high above the earth. For perhaps 20 minutes, this tiny sphere of water descends through the atmosphere, gathering speed, encountering air resistance, following the inexorable pull of gravity toward its inevitable impact with the ground. From the perspective of classical physics, this is a simple story. Gravity overcomes air resistance, kinetic energy increases, and eventually the drop strikes the Earth with a force determined by its mass and velocity. A straightforward collision with a predictable outcome. But we now know that this simple story contains multitudes. As the raindrop falls, it carries within its molecular structure the memory of its origins. Water that maybe once flowed through the Amazon rainforest, or rose as mist from the Pacific Ocean, or was locked for centuries in Arctic ice. Each molecule has traveled its own extraordinary journey through the water cycle, participating in countless transformations before finding itself part of this particular drop, falling toward this particular moment of impact. The drop's descent through the atmosphere is itself a continuous series of micro-collisions with air molecules, each encounter subtly altering its trajectory, its temperature, its internal energy. From the quantum perspective, the water molecules within the drop exist in superposition states, their exact positions and velocities uncertain until measured or observed. Einstein's relativity tells us that the drop's motion through space is simultaneously a journey through time, that its fall creates infinitesimal distortions in the fabric of space-time, adding its own tiny contribution to the gravitational field of Earth. As the drop approaches the ground, something remarkable happens. About 10 milliseconds before impact, surface tension effects begin to deform its shape. The perfect sphere becomes elongated, then flattened as air pressure builds up beneath it. The approaching collision announces itself through subtle changes in the drop's physical properties. And then comes the moment of impact itself. High-speed cameras reveal that the collision between raindrop and Earth unfolds as an intricate dance of physics lasting several milliseconds. The drop doesn't simply splat against the ground, it creates a crown of smaller droplets that rise briefly into the air before falling back down. Each of these secondary droplets carries forward some of the original drop's kinetic energy, spreading its substance across a wider area than its initial point of impact. But the story doesn't end with the physics of collision. The water from our raindrop seeps into the soil, where it encounters root systems of plants that have been waiting perhaps for weeks for exactly this moment of hydration. Within minutes, some of the water molecules begin their journey up through plant capillaries, becoming part of the living systems that sustain terrestrial life. Other molecules flow laterally through the soil, joining underground streams that connect to rivers, lakes, and eventually the ocean. Some evaporate almost immediately, beginning another cycle of ascent into the atmosphere. A few become incorporated into soil chemistry, participating in the complex mineral exchanges that support entire ecosystems. From one perspective, our raindrop's impact was instantaneous, a brief collision lasting milliseconds, ending with water absorbed into Earth. From another perspective, that impact initiated countless new journeys, launched molecules on paths that will carry them through biological systems, geological processes, and atmospheric cycles that may continue for decades or centuries. Which perspective is correct? Both and neither, and something more complex than either suggests. This is what we've learned from our long exploration of time and impact, that every collision is simultaneously an ending and a beginning, a conclusion and an initiation, a moment when one thing becomes many things, when linear time reveals its hidden dimensions of possibility and transformation.
The raindrop story is your story and mine, and the story of every conscious being trying to understand their place in the flow of existence. We are all falling through time, carrying within ourselves the accumulated history of our journeys, approaching moments of impact that will scatter us in new directions, send us toward destinations we cannot yet imagine. Sometimes these impacts are dramatic, the life-changing events that mark clear boundaries between who we were and who we become. But more often, they are subtle. The daily collisions between intention and reality, between hope and circumstance, between the trajectory of our plans and the resistance of the world. Each of these impacts contains the same magnificent complexity we've discovered in our exploration of physics and consciousness. None of them are truly instantaneous. All of them unfold across multiple timescales, create ripple effects that spread far beyond their apparent boundaries, participate in the ongoing transformation of reality itself. When we ask whether time stops when you hit something, we're really asking about the nature of transformation itself. We're asking how change occurs, how one state of being becomes another, how the continuous flow of existence accommodates the discrete events that seem to punctuate it. And what we've discovered is that transformation doesn't happen in an instant. It happens across all the instants, in the spaces between moments, in the quantum foam of possibility that underlies apparent reality. Time doesn't stop during impact, because time is the medium in which transformation occurs, the dimension that gives change room to unfold. Every collision you experience, every conversation that changes your perspective, every sunset that moves you to wonder, every loss that breaks your heart open, every joy that lifts you beyond yourself is a moment when time